बन गया है। तो वो तो फोटो आपको दिए थे ना बोला, क्या मंगवा रहे हैं छोटे वाला। अच्छा अच्छा। निकॉन का मान लीजिए छोड़ दीजिए, तो इससे किसी कंपनी में जो आप अभी जो मंगवाए हैं 100 वाला, वो तो आप देख ही दीजिए, तो इसमें लगाना पड़ता है ये वो कनेक्ट
Good afternoon, everyone. Good afternoon, everyone. Not delay. It's a live stream.
Yeah, I can hear you.
Yeah, okay. Okay. So, so we are back after lunch and a nice talk in the morning during the keynote session by Dr. Mukesh Kumarji, and who has rightly triggered the session by introducing the variety of materials and devices, how the materials can play a very important role in chip designing and various opportunities in the area of photonics and nanoelectronics. And in this particular session, technical session number 2, we'll be having 4 invited talks. And this session is a hybrid session where we can have the talk on from the people from academia as well as people from industry. So 2 from industry, 2 from academia. So let us begin with the industry side. And so from industry, we have 2 invited speakers, Ms. Alka Jaiswal. She's currently holding a chair of engineering manager and technical head at Intel Corporation India. And she has more than 15 years of industrial experience and has worked in areas like architecture, front-end design and verification. And she also leads the innovation charter in her group and is passionate in mentoring and guiding junior engineers. So I'm sure the students who are attending this talk, and she is going to talk about many things which are very useful for you. And I'm sure that through her experience and deliberation during this particular presentation, the concept of the achieving the target what we have decided in the beginning of this pre-conference will get achieved nicely. So I welcome Algaji and to this pre-conference, and I would like to you to please start your session now, your presentation. Thank you.
Thank you so much for the introduction. Good afternoon, everyone. Let me start sharing.
Are you able to share?
No. I'm not able to share.
What message you are getting? So in the bottom, share a screen.
Yes, I'm trying that only. Just give me a second. Okay. Yeah, I think I can share now. Let me know. Okay. Are you able to see?
Yeah, perfect.
Okay. So good afternoon, everyone. And first of all, I would like to thank Dr. Santosh and Dr. Anurag for inviting me and making me part of this wonderful session, which is of Fabulous and Fab Semiconductor Ecosystem Conclave in Madhya Pradesh. This is a great initiative by IIT Indore, Vigyan Bharati, and Madhya Pradesh Council of Science and Technology to bridge the gap between the industry and the academia. And this is a huge platform, and it will give a broader perspective about the technologies, about the science, and what advancement we can do in the state to basically achieve the requirements which are actually the goal of this entire conference and to the conclave, to equip the man force and to equip and to develop the skill set in the students so that we can have the chip design and we can have the semiconductor industries in the state as well. So now before coming to, I'm changing the slide. Let me know if it is coming up well. Has it changed? Okay. So before coming to the topic of the day, which is chip design, fabrication, and testing facilities, I would like to introduce where I come from. So I come from Intel India, and I would just like to give a brief 1 minute talk about what Intel India is. So Intel India was formed in 1999. So Intel started its R&D center in India in Bangalore in 1999. So it is almost 20 plus years of engineering in Intel India, and this is the largest design center outside of US. This is one of the non-manufacturing unit of Intel, and this is the largest one with an investment of $7.25 billion dollar investment. And we have competencies in almost everything in the design phase, right from SoC design to IP development and hardware and software platforms, architecture, front-end design, validations, everything. And we are creating technologies which are enriching the lives of almost every person on this earth, and breaking the barriers, be it in client or cloud, IoTG, data center, graphics, edge computing, 5G, and whatnot. So this I wanted to just give a brief intro that we have facilities in India. Yes, I understand there is nothing on in MP as of now, but I think with this conference and the initiatives taken by the MP government, I'm sure something will come up in MP as well. Now, moving to the next thing, which is like I want to start with when we are talking about the fabless and the fab semiconductor ecosystem. So, what actually we mean by fabless, or what is the difference between fab and fabless semiconductors, right? So, fabless, when we say the fabless semiconductor companies, so basically, are the fabless chip makers. So, they are chip makers, yes, but they are fabless. That means they do not have a foundry or a factory or a manufacturing unit of their own. Okay, so they are not making the chips themselves, doesn't mean they are not doing the chip design. So there are different aspects in the chip design. One is the design phase, the other one is the manufacturing. And that is, I think, what we are going to discuss in this session today. So fabless chip makers, they have their design units, but they do not manufacture it. Whereas fab or foundry, they are used interchangeably. It is basically a factory which is not doing the design, but it is doing the manufacturing of the chips or the integrated circuits, which is again used interchangeably. And now let me introduce you another term, which is IDM. So what is IDM? IDM stands for Integrated Device Manufacturer. And Intel, since its conception in 1968, from that time onwards, Intel is an IDM company. That means it is doing design as well as it is doing manufacturing. Okay, so we have our design centers, like one of the design centers is in Bangalore and other cities in India as well, and other parts of the globe. And we have our own manufacturing units in US as well. So this is what is the difference between fabless, fab, and IDM. And recently in the industry, there is buzzword, which is IDM 2.0, which many of you might have already heard, right? This is introduced by our current CEO, Pat Gelsinger, a few months back. And what it means, it stands for the evolution of the IDM strategy. It is to meet the global demands, which is increasing day by day, and we are hearing that we have a shortage of chips. So this is an initiative to meet the global demands, to increase the manufacturing capacity, to open up the Intel fab unit for the other fabless semiconductor companies, and also outsourcing some of the designs to the outside fab units, where we can leverage them and speed up the process, the entire process. Now, having said that, let me move to what is chip design. So I'm sharing a flow diagram here, basically, which has few bullets, but that doesn't mean that chip design is just this simple and only these steps are involved. Each of these circles which are being mentioned here is basically a domain and a wide, huge area of expertise within itself, right? Right from the specifications to the packaging and testing. And let me go one by one over this. So what do we mean by specification? Okay, so just in a layman term, specification means that you are defining the spec of something you want to achieve. Now, when we come to chip design, that means you want to design a chip, yes, but what do you want to achieve out of it? What are the features? What is the functionality you want? Or what is the reason why you're thinking to design a particular chip? So I'll take one example. For example, ADAS systems, which is advanced driver assistance system, right? So it is assisting the drivers and making the vehicles advanced in the autonomous driving. So if you want to design a chip for ADAS systems, what all you need? You or what is your requirement? What comes to your mind? Basically, you are designing that chip or having that kind of technology in place to avoid the accidents, the vehicle accidents on road, to avoid the collision, to maybe have a safe parking, to detect the traffic signals automatically. And sometimes maybe in the case of emergencies, you want your car or whatever vehicle you're driving to press the brake automatically just to avoid a particular scenario, or to detect any pedestrian who is walking down the road, right? So this will help you assist in the driving. So this all becomes the specification, along with like what you want in terms of area, the size of the chip, how much power should it consume, and all other technical specifications. So once the specification is defined, the next step is architecture. That means now you have to break down. You have a vision in your mind. You have an idea, but how to implement that idea and bring it on the silicon. So you will have to think that what all different components are required here. So the same example, what you need, you will definitely need some sensors. You will need some memory, you will need some AI, you will need 5G, you will need a display system, you will need camera, you will need lidars, radars, you will need hardware, you will need softwares, all these things, right? And multiple other things. So your architecture means you will come up with all these different components now which are required. And again, when I just want to reiterate one thing is that when we say chip, it is not one single thing these days. When we say chip, it is basically the system on chip. So we are designing the entire system on a single chip, integrated design, and that is what we talk these days. So and which we call SoC, right? So there will be all the firmware, hardware, software, all these aspects also will be involved in the chip design these days, because we are designing the entire system on the chip. So once we have the architecture, we break it down further into the micro architecture. We also define that, okay, what part we can implement digitally, what part we have to implement in analog, which is the circuit design. And once we have this demarcation, and this is again not done by one person, right? There is a whole bunch of people who are sitting and defining all these things. So, and it requires lots of knowledge about multiple other domains. So now I'll talk more on the microarchitecture and logic design. So when this architecture is broken down into the microarchitecture, and then comes the logic design part of it, basically logic design is the digital design, right? So we have many hardware description languages like Verilog, like System Verilog, like VHDL, which we use and we write a code out of it. It's a program which is more readable by the human mind, and we can just put on whatever logic we want in a very good presentable way and understandable way. So it gives us that flexibility. So once you have the RTL code, and similarly for the circuit, analog design, you will have a circuit implemented in the form of SPICE or a SPICE like that. So once you have the logic design or you have a circuit design, the next thing is to verify it. Again, verification is not a simple thing. Lots of resources and lots of time goes into this, because this is a very, very critical step in any chip design, because what we do is a very, very expensive work. We cannot afford to have bugs on silicon. We cannot afford to find not only on silicon, but also late design bugs. So it is very, very important to do a thorough job at design level, and then verify it and make sure that whatever design we are delivering is of good quality, it is meeting the specs, and all the checks are being performed. Apart from the verification, there are a lot of quality checks also we do. And then when it comes for the logic design, it comes to synthesis. So the logic design, when we are saying synthesis, basically it is converting the RTL code into logic gate netlist. So the netlist is generated. Now to generate the netlist, there are other things also. These, because it is a system, it will have multiple clocks, it will have multiple power domains, it will have you will have to provide the timing constraints to see that whether your timing is met or not, or what constraints you want to give. With all this information, the synthesis is performed, and then a netlist is generated, and then you perform a timing check to again see that yes, you are meeting the timing which was expected according to your architectural spec, right? And then if any of these things are not meeting, you again go back to the design. There are techniques to meet this or to modify the design, and all this takes place. And similarly, in the analog design, you will have the schematic, and now comes the integration part, right? You will have to have the your schematic along with the netlist, you combine, and then again you have to verify that now with all these things integrated, the entire system here in the front end, are you able to meet the specs? And that is where the gate level simulations come into picture. So like we have logic verification, again you do the same simulation environment, and you run the sims on the gate level netlist now, and along with the UPF, along with the timing reports, everything, so that you ensure that everything is in place. So till this part, it is the front end, right? And then comes the physical design, which starts from right from the floor planning to place and route. So you put on all the pieces together, you do routing, you do placing everything on the chip, and then again you have to perform certain checks, which is like DRC and LBS, which is design rule checks, or the layout versus schematic, to ensure that yes, your metal spaces are okay, your layout is matching the schematic. And once all these things are done, till this physical design we also call design for manufacturing, because this is the last stage in the front end design. Basic, not only front end, along with the physical design, but this is the stage till where most of the fabless companies also work, right? And then after this, there is a collateral which is generated, which is called GDS2, which is given for the fabrication. So far, whatever I have told is part of the chip design, and then fabrication and packaging and testing it itself is a very wide topic, which I'll try to cover as much as I can in the given time at a very high level in my next slide. So I'm hoping that the pace is okay, and people are getting the gist of that. That chip design doesn't mean only RTL coding. It doesn't mean only floor planning, or it doesn't mean only microarchitecture or circuit design. It is a lot more than that. Okay. So now moving on to the next slide, I'll try to cover the basics of the fabrication. And so whatever I discussed in the previous slide, that is what the fabless companies do, and the IDMs also do. What I'm going to discuss now is what happens in the fab. Okay, so which is fabrication. So fabrication, it starts from the wafer. So what is wafer basically, right? Wafer is a silicon disk. It is and silicon is obtained from sand, and it is there in abundance. So the silicon is extracted from the sand. It will have lots of impurities in it. So what we do is we heat the silicon to at a very high temperature until it reaches its molten state, and then the impurities are purified, and then it is rotated, and then a cylindrical shape of silicon rod is being formed, which is basically called ingot. And the process is called the floating zone process, or the Swarovski process as well. And once you have those ingots, the cylindrical cones, you rip off the top of that cylindrical cone, and then you start slicing the below part with a very sharp diamond saw blades, very thin layers, and they are very shiny, very glossy layers, which we call the wafer. Okay, and so far what happens is this is non-conductive, but for the chips what we need is semiconductor, right? So then the next stage comes, which is photolithography. So now we have the wafer, now starts the process of making the complete chip. So photolithography, it is a process which involves multiple steps, and what I have shown here below, these steps are the part of photolithography. Okay, and on the right side, I have this diagram which you can relate to. So the bottom is the silicon, and now what we do is the oxidation. Oxidation is creating a layer of oxygen on top of the silicon. It forms the silicon dioxide, and it is kind of a protective layer. And there are multiple processes which are done for the oxidation. There can be dry oxidation, there can be wet oxidation. The difference is that when we say dry oxidation, it means that only the silicon is exposed only to the oxygen, and a very thin layer of oxygen is formed on top of the silicon. And when we say wet oxidation, that means along with the oxygen, the silicon is also exposed to vapor. So it penetrates slightly deeper and it forms a thick layer of oxidation. But what we get is the SiO2, which is silicon dioxide on top of the silicon. And you can relate it to or compare it to any iron which is kept outside, and when it comes in contact with the oxygen, a thin layer of rust gets formed onto it, right? So it is similar to that. And the next stage now comes the photoresist coating. So photoresist coating means actually it is a coating the substrate, the whatever we have now with this SiO2, that substrate with the light sensitive organic material to form a pattern coating on the surface. Then a pattern mask is kept on top of it. Now, what is mask? It is a photo mask. And in the previous slide, I talked that the collateral which is delivered is the GTS2, right? Which is it is a database file format, which is industry standard. So everyone follows it. It is basically used for the data exchange of the ICs, and it is a binary format, and it represents or gives the details of the planar geometrical shapes and text labels and informations like that, with which the photo mask is formed. So GDS2 is used to create the photo mask, and those masks is kept on the photoresist coating, and then the stepper exposure stage is performed, which is basically exposing the entire thing in the UV light. And what happens is that the part of the mask which is covered, so there are two things here. Now again, the photoresist can be a positive photoresist and a negative photoresist. So for positive photoresist is the photosensitive material is degraded by the light, and the developer will dissolve away the regions that were not under the mask, or basically that were exposed to the light. So whatever is exposed and the in which whatever is present inside the mask will retain the photoresist coating, other will be dissolved. And in negative photoresist, it is just opposite of it. So whatever area, and it can be seen from the diagram which is shared here, that the area under the mask will the photoresist coating there will be removed, and the rest of the places will have the resist. And then is the development, photoresist development, and a baking, which is also called the soft bake, which is at the slightly low temperatures, it is heated. And then the acid etching happens, which is etching is basically here, you can say it is kind of acid wash with some chemicals, which is performed so that all the other impurities and the unwanted stuff from the complete top layer can be removed, so that only the required mask related stuff, which is basically the circuit, the design which you want to be there, should remain. And after this photolithography comes the process steps, because ultimately what you want is transistors, resistors, capacitors, inductors. That is what make the VLSI design, right? And that is what is there on the chip. So there are different processes again, like diffusion and ion implantations. Diffusion, as the word itself says, that moving the particles from a highly concentrated region to a low concentrated region. Ion implantation is done using the guns, and it is like bombarding the ions on the substrate with a certain force, with a certain amount, so that the right amount of circuit can be obtained on the substrate. And then the deposition, which is depositing certain layers where you can add buffers and wires and other stuff, so that deposition happens. And then again, there is a plasma etching, as I told earlier as well. It is like cleaning the unwanted thing. So now instead of acid, you're using plasma light, and you are exposing your substrate onto that, and then you're cleaning it up. And then comes the planarization, which is like smoothening the surface. Now because you have to make it very uniform, very shiny, and there should not be irregularities into that, and there should be no impurities into that. And then finally that is given for the assembly and packaging. Again, assembly and packaging are themselves very wide topics, which I won't be able to cover in this session definitely, but this is how the entire fabrication process happens. Okay. And coming to the last part of my session, which is testing facilities. So we have talked in a previous slide when I was talking about the chip design that we do verification. So we do verification at almost every stage, right? Once the logic is designed or the circuit is designed, you do verification. Once synthesis is done, again, you do verification. Once the layout is there, again, you do verification. Basically, you're cross-checking that the design is meeting the specs. Then what testing is remaining, right? That might be the question. So what remains is, because that is all part of the chip design. Now, what happens in the fab is a completely different thing. And there can be defects because of all these different fabrication steps, which we discussed in the previous slide. So there can be physical defects, there can be electrical defects, there can be logical faults also. So physical defects, for example, the mask which you're putting on the substrate, the photo mask, that can be contaminated. It can have scratches. There can be process variations. There can be other abnormalities. There can be errors introduced during the oxidation or during the photolithography or in the silicon substrate itself, right? While you're doing etching or doing other processes, because you pass on through multiple tools and expose it to many things, there can be impurities, there can be scratches, there can be defects introduced because all those things. And then there can be electrical defects. You can have shorts, you can have opens, you can have some sorts of resistive faults also. There can be regions in the chip where the current is more, it's taking more current. There can be regions where the voltage is going above the threshold voltage, and there can be logical faults also. That's your logic is just stuck at 0, it is stuck at 1, or there can be delay faults also, right? And all these needs to be tested. So once the silicon is there, you have to check all these things, right? When finally the chip is designed, you have to go through all these tests, and there are many tools, many EDA tools which perform these kinds of tests. There is IDDQ testing, which is done in the fabs, which is basically to check the current. Then there are ATPG patterns there, and there are lots of design hooks actually, which you provide while designing the chip itself, which is called design for debug, so that you provide the hooks so that it makes it feasible when you are checking on the silicon. You will have the right observability, and you can reach out to the proper metal layers and the logic inside. And there are tools and there are oscilloscopes which can go and pinpoint and see where actually the thing is stuck, right? And then there is design for test with testability, again, where you have ATPG patterns, you have scan chains running across all the flops, so that you just pass on the patterns and see that, okay, there is no stuck at 0, stuck at 1 faults. So there are so many aspects when we talk about the chip design. It's not only coding, it's not only designing the circuits, and when we talk about fabrication also, it's not about just having some silicon and putting something into it. And everything is so expansive and so time consuming here that you cannot afford to have faults in these kind of things. So all this is very important. And with this, I want to close my session here, and I'm open to questions if there are any. And then thank you so much for giving me this opportunity, and whatever in my personal capacity I would be able to contribute to this MPVS, I would definitely like to be there.
Thank you so much, Alkaji, for introducing the complete concept and fundamentals of the chip design and what fabrication is, how people should go for the verification and then go for the testing, why they are so important, and various steps we have nicely talked about. I'm sure the students who are attending this session, this particular presentation was very useful for them. And the people who are actually not of this domain directly, and they get complete flavor what actually the chip design, fabrication, and testing is. So thank you so much. And I'm sure if anybody has a question, 1 or 2 questions are possible.
Yeah.
The attendees.
Yeah. So yeah, madam, this is Jawar Singh.
Yes.
So I just have one very simple question: how this AI is penetrating this chip design?
AI
As
is okay. Yeah. So there are, see, when we talk about chip, there are multiple units like CPUs, GPUs, and now we have VPUs, which is the visual processing units, right? So AI, AI, there are multiple IPs which work on AI because they have the algorithms running, machine learning is done.
so let me
So
just let me more precise actually.
yeah,
So
yeah.
specifically, you mentioned couple of steps. There are plenty of steps involved, and also different level of abstractions are also involved. So specifically, if I focus only on the digital chip design, let's say, so how this AI can expedite this design cycle,
It
and
can,
also
it can, and this is a very good question actually. Yes, it can definitely help. AI can be used to reduce the design cycle for sure. For example, as I told that there are many steps in the verification itself, right? So you can speed up the verification. You can have the algorithms which can, and you can train the tools also, and you can have algorithms in place which can just run through and see that what are the common faults, and maybe they can correct the design itself, right? Or they can give you the solutions or suggestions. So the time the and there are many places where the human errors are introduced, right? So with the help of AI you can reduce those human introduced errors as well. So
right.
this will definitely improve the quality of the design as well as reduce the design cycle. Yeah.
So it is being used in Intel or just in general, let's say, or any other company, let's say.
I don't know about any other company, but yes, we are definitely exploring
Okay.
where we can utilize this. Yeah.
All right. Thank you.
Yeah.
Okay, so one more question is from the attendees, Mr. Abdullah. He is asking about what is your advice for freshers, especially for front-end design. So would you like to give
Okay.
advice to those who are interested in this?
Yes. 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 So for freshers, actually, my advice is that your basics should be very, very thorough. Okay. So please focus on your basics. Have the basic understanding, have the right attitude. See, you should be. What I have seen is generally when freshers comes, they have some kind of thought that this is what industry does, right? Based on whatever they learn in the academics, but they should be more open to understand that it is much more. There are many tools, there are many aspects of the design. So what I have seen in general is that people think that design means RTL coding. Okay, and that is a misconception, I believe, in my view, because coding is one aspect of the design, right? But chip design is basically, when you're talking about VLSI design, it is more on the architecture or the micro architecture, how you can convert it into the gate level, how can you can optimize the design, and how can you improve the qualities. So freshers should be open to learning all these things. Second, they should have their basics very, very clear, and they should be open to learning as much as they can. And they should increase the breadth of their understanding as well, along with the depth.
Okay, thank you, Algaji, and
Yeah.
for nice presentation and interaction with the attendees.
Yeah, thank you so much.
Can I ask a question?
Subhashi, we have other talk schedule, so
Okay,
you can directly chat with the ma'am, right? So she must be able to answer the question, but because other speaker is line up, so these are the people from industry, so they must
no
be
issue.
Yeah.
Okay. Yeah, thank you.
Okay, so we have other speaker in this particular session, Mr. Deep Sahgal, and Mr. Deep Sahgal is basically head the VLSI division at SCL India. Huh? Bad. Okay. Share नहीं वो सर ने भी share कर रखा है ना. So before your presentation, Deep ji, can we just introduce yourself?
Am I audible? Am I audible?
Yeah, you are audible.
Thank you.
So Deep ji has more than 17 years of experience in designing, and he has worked upon many projects in various domains, starting from 3 micron to 18 micron 0.18 micron of technology nodes. And he has been involved in multidisciplinary project for development of infrared camera systems for night vision application. And Deepji has graduated from NIT, REC, Surat, Gujarat in 1996, electronics stream, and joined the SCL in 1998 as VLSI design engineer. And his dominant field of interest has been in analog design in all these years, apart from design, work at levels of project, number of project I have already said. So with this, I would like to invite Deepji for his interaction with the attendees and what content he is going to deliver on VLSI design and testing. I'm sure the kind of, the extension what Alka has, introduced to the audience. Yeah, thank you.
Thank you, Dr. Anurag. So my greetings to everyone who is attending this conference. And it is a good initiative, a very timely initiative by all the dignitaries, seniors of Madhya Pradesh administration and the academia there. My talk will be a walkthrough, basically a walkthrough on the VLSI design and testing, and the time allotted is, I think I can only handle the overview of the things. So let me first introduce, I come from semiconductor laboratory. So the semiconductor laboratory actually is situated in the Mohali, Punjab. It is bordering Chandigarh, and it comes under the Department of Space, Government of India. We are mainly dealing with the space electronics and the other strategic sectors of our country. The main activities happening in the SCL is we are into the VLSI, MEMS and optoelectronics, design and fabrication, development of various process technologies, high voltage technologies, and the LDMOS and other opto technologies. And we are also into the testing and packaging of the VLSI, of MEMS and of optoelectronic devices. There is a system engineering and assembly happening, and there is a full level of reliability and quality assurance, which is within the premises of our SCL. So under one roof, we can see all these verticals starting from the process, the design, the fabrication, the testing, the packaging, and finally the reliability and quality assurance, which is a very, very key aspect in any of the high reliability programs. So I will say that SCL, okay, this talk is basically on the fab and fabless, and the previous speaker was also talking of IDM. So in a short way, I will introduce semiconductor laboratory only as the IDM under the Government of India, which is doing all these activities, verticals under one roof. Now, I would like to shift on the microelectronics evolution a little bit. So we all know it all started when the India was getting independence, 1947. And we started from the BJT transistor, and we went to the 1957 integrated circuit. 60s, we went to TTL family. 70s, there was the NMOS microprocessor, the first microprocessor from Intel only. And the CMOS came into existence somewhere in 1980s. But at the same time, the industry experts were predicting the death of the analog, because they saw everything can now be taken up by the digital, and digital signal processing can be everywhere. But what we have seen, what we have witnessed, we are in 2021. CMOS is also continuing, although many hurdles were expected in its journey, but analog is still continuing. So it is a very fascinating industry in short. If you see the microelectronics, no other industry has really survived the exponential growth for over 60 years, the 6 decades. Even the plastic, stainless steel industries, they also could not come up to the exponential growth survived over the 6 decades, more than 6 decades. We started from 30 micrometer, we are talking of 3 nanometer, and we are even not seeing any end to this in the foreseeable future. What has happened? Over the years, if we see the journey of this industry, we can have a 30% shrink or 0.7 times improvement in the minimum dimensions or the finest pitch or the half metal pitch or the gate lengths over the cadence of 2 years. So we can extract certain information from this slide. We started from BJT. But why we came to CMOS? BJT was once the dominant device in this field of industry. But over the years, ultimately because of the power issues, BJT had to go away. BJT was not, it was a area consuming device, but more often it was a power consuming device. So they moved to NMOS. NMOS was faster, having lesser power consumption. But even the NMOS could not survive. They went to CMOS. And ultimately, CMOS also is now not able to survive the power consumptions, or it is becoming more like its BJT cousin. But still, in this battle between the BJT and CMOS, much has shifted to CMOS. But now we are again seeing the coming up of the BJT device in the terms of 3-5 compound semiconductors. What has happened? See, you can ask that why this industry has survived over the 60 years. One of the key aspects which has actually governed this all CMOS evolution, or you call revolution, is the scalability aspect of the CMOS. It cannot be ignored. CMOS was, and it is, salute goes to the lithography engineers actually, who has really made that simple equation of the Rayleigh's criteria, K1 lambda upon Na, or Na is n sine theta. This simple equation was so much chased, was so much improved, that they could have the scalability even up to the present generations of 7-5 nanometers. And you see, the Dennard and the team gave a very simple formula for the scaling. They said that geometric feature, let it be reduced by 30%, voltage, let it be reduced by 30%, substrate doping, let it be increased by 40%, everything being governed by the S equal to √2. Although it is an ideal field scaling on electric field scaling theory, but still we can have some glimpse from this that these basic things have made the improvements in the delay factors by 30%, or the speed by 20 to 40% practically, average power getting reduced by the 50%, and the power delay or the energy getting reduced by 60%, 65% every generation. So this energy, you see, energy per transition is an important. We are talking of green chips, and it has gone from picojoules even to the femtojoules and crossing the femtojoules, energy per transition for a transistor. So this 30%, 50%, 65%, this has actually fueled the industry. The CMOS has been its own, it has refueled its own journey, and there is no end so far. CMOS scalability and what is happening on the constant scaling, it is not actually pursued always, although Dennard started with that, but industry has gone up to the mixed scaling. It is a constant voltage, it is a constant electric field. In some generations, it was more prominently the constant electric field. Again, it became constant voltage scaling. So, but certain things are, we should realize that certain things are not scalable. Silicon band gap is not scalable. Built-in voltages are not scalable. Threshold voltage is also having a limited scaling. Even the sub-threshold slopes are not scalable that easily. And supply voltages are again governed sometimes by the board standards, and we cannot have the things at our will. Had it been a constant electric field scaling, we would have the supply voltages in the range of millivolts. But so this is the journey which the CMOS has advanced right from its inception. There are certain pros and cons related to the scaling. Scaling is basically why we are going for that. Everything is getting improved. You have a smaller transistor. Smaller transistor is also faster. Smaller transistor is basically cooler. Smaller transistor is basically cheaper. But I will come to this aspect later on. Let us see some disadvantages associated with the scaling. The leakage power has increased over the years, and CMOS is taking the shape of BJTs. The dynamic range for the analog designers is getting sacrificed with scaling. ESD susceptibility is actually, device is basically a very small, but the ESD voltages have not scaled over the years. You still have 2 kilovolt, 4 kilovolt, 8 kilovolt human body models, even the CDMs. And the energy which is imparted to this simple small device is too much. and ESD susceptibility is actually going, it is a big area. How can you have the high ESD survivability? Process variability is again becoming too much. There is very less dopants which are remaining in the channel, and you have a greater variability of the threshold voltages and other parameters of the device. So the life of the designers is not that easy when they are dealing with the newer generations of the process. But I am putting it in the simplistic manners. I am also talking of the red heart. In the upcoming slides, we will have a better view of this red heart aspect of the electronics, but sufficient to say here is that it is total ionizing dose, how much dose it can really accumulate and can still perform a simple CMOS gate or a simple MOS transistor. So the TID susceptibility, total ionizing dose susceptibility is actually improving, but the single event effects, a single dose of high energy particle, when it crosses the drain and junction regions of the MOS transistor, it can play a havoc on the chip. And SE susceptibility is actually going downside with respect to scaling. Let us have a broader overview. We cannot have the digital world alone. We cannot have the analog world alone. Digital and analog process generations have gone in a different manner. You see, I am today standing at the digital. Maybe it is a minimum dimension is L, and there is no high quality passive available. Tomorrow, I may have a generation N+1 digital with dimension and the speed capability power, everything improved. By power, I mean dynamic power. But there is no high quality passives. And it takes almost 2 years for this previous generation to come up to the high quality passives, but still with the minimum dimension of L. So there is a trade-off studies. You see, I can have a chip designed on this generation N+1. Microprocessors and DRAMs have governed the industry. But if you see from the analog angle, from the high voltage angles, they are lagging behind their counterpart digitals of this N+1 generation. What is analog process actually? Analog process cannot be a process which is not having a high quality analog modules. It must be incorporated in the baseline digital process. What are the high quality analog modules? Just a simple glimpse of the resistors, the capacitors, the inductors. They cannot be done away with. Analog is still relying upon these basic elements along with the transistors. So let us have a few glimpses of what we are having in the SCL as 180 nanometer process, 40 milliamp to 1 kilo ohm square per square of sheet resistivity, and the capacitor types going from, you can see 0.07 to 9 femto and all types of, even the intermental MFCs are also there. Inductor types 2 to 12. How will you make the inductors? You can have the top thick metals, or you can have the bond pair at the package level. In totality, if you see, this comes out to be the 80 types of 80 count of devices with the various devices under this category. Now you see, we can have the 80 devices, but how analog design engineer will really choose the things? So there is a study. I think the basics of the industry has not changed over the years. One cannot go away with simply going to the PDK, taking one transistor and starting designing. He must have that how many types of transistors are available, resistors are available, what is their properties, what is their density, temperature coefficients, voltage coefficients, matching figures. Everything needs to be carefully studied before we go into the high-end design chips. So putting it in a basic perspective, I will only say it is design framework still remains right from what it was in the beginning. We still want to have the targets, and there is an electrical design aspect, there is a physical design aspect, and you have to have an entry at the electrical level, you have to have the entry at the physical level, and you have to devote a great amount of time, both in the verification side of the electrical, as well as verification side of the physical, as well as the layout parasitic extractions, gone back to the electrical design and done the simulations and verifications. It is an iterative loop. It is a local iterative also at both places, and it can be sometimes even the iterative to the right from physical to back to electrical. So there is one more need coming. once you are transforming the design from the electrical to physical, what is physical? It is a layout, basically. It is only the mixture of the geometries. So you have to have an equivalence check. How will you make sure that physical is actually making sense with the electrical, or what was your original intention? Ultimately, someday you have to make the decision to make a tape out to the chip to mass data preparation team, and thereafter it will go to the fabrication. And one more thing, targets. These appears very simple, but many of the things are lost when we do not understand what are the targets or the basic specifications and features we are really wanting to design. And do we really understand the application scenarios where these chips will one day be made use of? What is being exchanged between the fabless and fab groups? So we have a design house, which is a fabless house. We have a pure play foundry, but they can interact. And PDKs are the keywords, the process design kit. Without this, I don't think that nowadays designs are ever possible. These are the actually productivity enhancers which are coming from the foundries. What are they going to give to the design house? Basically models, the rules, the parasitic extraction deck, the technology files, P cells, the symbols. Everything comes in the form of a well-knitted kit to the design engineer, and he can use it as per the EDA tools available to that design house. And in return, they have to give back to the foundry. We were talking of tape out. This is the layout database, GDS, which is now, it was called tape out because it was being made on the tape, but now it is actually electronically transferred to the mass making teams. And DRC and DFM clean, the design should be in the last. So let us talk of what you can build upon this basic PDKs. So you have now PDK. You can use this PDK. You can build your own library, or even the library can be procured, or maybe on the cost basis from the foundries. So we have the slow fast corner. These libraries are basically the semi-automatic designs or the semi-custom designs which are being done by the digital engineers. Temperatures and everything, all corners are there. We have 540 cells. We have a basic cell height of 5.10 track library, and we have NLDM and NLPM models, as well as the CCS models. Memory compilers, this is another unit. You cannot go away with this. See, nowadays, even more part of the chip, the high-end chips, is memory, and you need so many memory cuts when you actually go for the digital designs. So how will these cuts be generated? You can generate it with the automation program, and which even can be developed inside the design house. And you can have a layout generator, for example, which can take maybe from 2 minutes to 17 minutes to generate the memory cut of this much of size. Let me walk through just a basic backend design details. It is actually a processor chip, but what I'm highlighting here is these all blocks. They are the memory cuts which are available. These are the power straps which are there, and somewhere here the power pads or the IO pads will be sitting. Now this floor plan has been done now for your chip. The next place what you will do is the placement of your basic cells. Now once the cells are placed within the areas available inside the around the memory blocks, you go for the clock routings. This is the clock coming from this pad, routed all throughout the chip, and then you go for the final layout. This is what the chip will be appearing once. This is a 4-metal chip which will, when you will be taping it out to the mass data preparation team. IR drop maps look like this. See, this chip is basically having 194 milliwatt of power, and the maximum IR drop, the power line drop, which is happening, is 37.8 milliwatt. If you have 1.8 volt of power, 10% comes out as 180 millivolts. So this chip is well within the 5% even of this of the requirement. I will also highlight the analog design peculiarities. It is, see, the industry experts told that analog design may not be needed at all. But analog proliferation, if you see, it has gone to the sensors interface, high-speed digital, memory designs, power delivery, wireless, wireline, everywhere it has been proliferated. High-speed digital, I want to highlight. See, ultimately, when you go for a very high speed, or the clock cycle times are getting reduced, the rise fall times are also getting reduced. Rise fall times normally stay from maybe in the aggressive design 2% to 1% to even 25% of the cycle time. If these rise falls are really getting smaller, we have a very clean relationship where the rise time is related with the bandwidth by 0.35 factor. Therefore, we need to feel that if the bandwidth of my interconnects are not enough, I'm going to have the signal integrity problems. It may be in the form of reflections, it may be in the form of LRC ringings, but you have to deal with the signal integrity problems. And high-speed digital is taking the shape of actually much of the analog design. You have to have a very powerful foundation on the analog design to deal with the high-speed digitals. Analog design again is having very wide range of parameters. This is one of the big problem in analog design. You have to deal with multiple parameters as I have listed here: linearity, bandwidth, range, power, noise, everything coming here. And it is having a multi-dimensional trade-off among these parameters. So you have to sit, you have to really understand your basic op-amp even, that how much trade-off I am going to incur in the VCO, in the PLL, and in the stability. Every issue you have to deal with. So it requires a good understanding of device characteristics, biasing, modeling, even the layout effects. You have to really decide when we are having a design, analog designer has to deal with all type of multi-fingering and all type of dummy placements, all type of commons and interdigitated, and the substrate effects they have to think of, how they will really make the power delivery to analog design. It is sitting very close to the high-speed digital ultimately, and ultimately it makes highly analytical in nature. So therefore, I would like to say that the fundamentals of industry have never changed. You have to have a very high grasp on these basic issues till we go to the high-end chips. There is one more requirement of the space electronics, very peculiar requirement, but this requirement is also actually not only peculiar to space, but also to some medical electronics, to the high energy nuclear experiments also. Radiation, it has a strong impact on VLSI, shaped the development of space electronics. You can see this transistor. This is not a conventional transistor. Here you can see this is the drain region, this is the source region of the transistor, and this is the guard bar all around. Now this source and drain, and there is a gate, which is this gate, this red one turning to yellow one, and now this gate is surrounding the complete drain. So there is no STI cutting between the drain and the source. And this STI edge is absent actually. Since it is absent, you won't have the charge accumulated because of radiation leading to the intra-device leakage, and guard bar preventing the inter-device leakage. And SE, single event effects, are the effects which are because of some particle going through this region. And ultimately, if the one is stored, the particle energy can be so much, electron hole pairs generated can be so much that even they can flip the logic 1 to logic 0 or vice versa. So again, it leads to development of standard cell library, where the cells are very less, 56, developed within the SCL and being used in the space programs. Now, miniaturization is the key word. We need to go for miniaturization. One reason I can tell you for the miniaturization is, I come from the space domain. See, ultimately in the launch vehicle, the electronics is sitting in the last. By electronics, I mean the satellite and the payloads inside the satellite. So it is sitting at the nose, and just beneath it is the full range of electronics sitting. Now, miniaturization means swap. Size, weight, and power, everything is being reduced. If you reduce the weight, which we often not think of, but if you reduce the weight by 1 kilogram in the equipment bay just beneath the satellite, you can actually save 1 kilogram and transfer it to the payloads, transfer it to the mass of the important equipments, which will do the job in the space. So it is 1-to-1 ratio transfer. Therefore, we can have a programs which can go for a multi-chip modules where we have performance, volume reduction, mass reduction, power reduction, even the heterogeneous integration. You don't have time to develop all the technologies. Why can't you mix the chip on the package? Why can't you have even the 2D stacks, maybe 3D stacks? We don't have 3D stacks right now. We are under development with respect to 3D stacks, and it is expandable also in the future. But multi-chip modules have their own disadvantages. Your dies should be highly known good dies. Yield should be very high. Testability of the die is a challenge. Power, signal integrity, and thermal integrity, these are the key aspects when one go for a miniaturization, joining many chips on a package. It reduces the RLCs of the parasitics of the packages. It increases the speed actually. This is one example of what has been developed in the SCL, a complete 16-core Sigma Delta ADC, which has been inducted in the launch vehicle. Now, this is the package, but inside this chip, you can see the 16 cores of Sigma Delta ADC sitting here with the digital electronics somewhere here and the LDOs here. So these type of chips, the multi-core, we talk of multi-core processors, but the concept remains same. You can have a multi-core chip in any domain. And this is the example which has a huge saving on the board. If you can put the cores in a one chip, you can have a very small form factor boards, which actually saves the weight, which actually saves the power and transfers it to the payloads. Now, this is the range of designs completed. As I told you in the beginning, we are doing the VLSI. We are also doing the optoelectronics, even at the cryo, because sometimes the requirements are at the 77K temperature operations. We are almost in the ADCs management, power management, RHPD, memory chips, and some very peculiar chips are not. They are the interfaces, digital interfaces, which are actually required in the strategic sectors. Not only this, the SCL as Professor Anurag was in the beginning saying, it is one of the industry which is owned by the government of India, which is at 180 nanometer and which has given its PDK to 70 academic institutes all across the India, length and breadth of India. 100 designs fabricated for academia. These are the examples of the design by various academic institutes. 65 MOUs with R&D units and leading academic and special manpower development program support. So all in all phases, 1, 2, this is the third phase of the SMDP going, and we are all supported this academia interactions and academia institutes. Just have a VLSI testing overview. Testing is basically, now your chip is fabricated. You have taped out, so after some time it appears from your fab, it goes to ET, quality, and then it ultimately comes to electrical testing. It goes to two phases. One is the wafer sorting. It is tested on the wafer and then it is made as a package and again tested on the package. After wafer sort, wafers are cut into individual die, good dies are assembled into packages. Now to maintain the integrity of this process, you again have to test at the package level. So there are two types of testing going on. Now, what is the role? What is the aim of electrical? Determination whether or not the device has some fault, but this is not the go or no-go type of test. You also have to go for full device characterization, full signature of the device over the temperature range, over the voltage range, over the samples to understand what is happening in this is a big exercise. Diagnosis. Now, if this device is not performing, you set up the failure analysis boards, you take the data to the FAs, you take the FMECA is the another term, or the failure mode analysis the another term, where you are determining the errors that have caused the non-performance of the DUT and diagnosis of these errors. Just the glimpse of the resources which are available within the SCL also, and which will be needed by any testing house. Say this is the probe card. Now here we have the probe needles, which is sitting, and here's the ribbon cables that are connected with these probe needles, and the chip will be somewhere. The wafer level chip will be somewhere here. Now this chip will be. This again is an example of a prober, which is having a probe card. This same probe card, now this is the machine where the wafer is inserted, and this prober is actually holding the wafer as well as making a connection with the probe card, the ribbon cables going to this tester. These two are the testing machines, and it will be docked upon this prober, so to have a very small interconnect lengths, so that you can have a high speed testing carried out. This is the ultraflex tester which is available, and it can test up to 400 megahertz. It can test maybe, if I remember correctly, it is 256 pin ultraflex tester. Results of testing. If you have to characterize, as I said, full device characterization, 14-bit pipeline ADCs, you have to have the DNL, INL plots, you have to have the SFDR, SNR, all announced. Imagers, you have to, this was a one imager, this was a development cycle only, and we could have the pictures from this imager. Now, what is the end result? End result of this whole exercise is actually the devices delivered to the end user. It can be 24-bit sigma delta ADC, which we have delivered to our space centers, 14-bit 10 MSPS pipeline ADCs, CMOS camera configuration. This is a digital ASIC. This is the pure analog ASICs. Now here, this ASIC was actually in the lander, in the Chandrayaan 2. This is the 2 Mbit SRAM, and here we have an optoelectronic device, which is 12K time delayed integration CCD imager. So the whole thing boils down to, can I give a really end product, fully qualified to the military and the space levels, and qualified to radiation hardened levels, and then it will be finally utilized in the needs of the country and in the strategic programs of the country. So with this, I thank you. I thank you for your attendance, and again, special thanks to Dr. Santosh and Dr. Anurag and the organizing team there. Thank you.
Thank you, DG, for finishing in time. I'm sorry, I just squeezed the talk. Requested you to squeeze the talk, but I know that very nicely you have introduced that what SCL is basically doing and how you people are contributing in the national mission of developing this country into an electronic manufacturing hub, and in various domains how academia can get collaborated with you people, and you have shown that nicely, that how various designs have been created by the various institutions, and I'm sure that the research scholars and the students who are attending this session, they must get triggered, and they will also start working, and they will also start sharing their designs for the verification and testing to you, and I'm sure you will be helping them. So one or two questions are possible, because other speaker is already in queue. So if anybody has a question, one or two question.
Can I have one question?
Yes, Subhashi. Yeah, Subhashi. Yeah.
Thank you so much. At this semiconductor laboratory, suppose we submit a GDS layout. So through multi-project wafer facility, can they give chip manufactured from that section?
Yes, Subhashji, this is possible, and this we are doing right from past many years. What you can do is you can contact the either to SCL or directly to the chip center in the Bangalore, and you can route your GDS basically from the chip center to us, to SCL, and we will definitely fabricate in the MPW programs. We have a dedicated MPW program for academia, and we will give you back the samples of the dice.
Okay, great. So we have to use the your PDK or some open source PDK. Like I used to design on Sci Epic PDK, basically in silicon photonics. I used the scale layout. On the scale layout, I used the Sci Epic PDK developed by University of British Columbia by Professor Lucas. So that is the PDK which is available to us. However, other PDKs, being industrial, confidential things, we are not able to access. So what about this PDK developed by this laboratory, semiconductor laboratory?
See, one thing is PDKs are highly tied to the foundry that we are targeting to, and our PDK is not definitely a PDK from the photonic side. It is a PDK from the electronic side, and we can share the PDK with you. But so far, to give you the feedback, the photonics devices have not been tried here. I mean, photonics on silicon. So if that PDK is with you, it needs to be tuned actually completely, or rather redesigned to the SCL foundry. But electrical PDK is a completely silicon proven, and we can share it with you.
Okay, thank you so much. I got some email there on website. I will communicate definitely.
Surely,
Thank
sure.
you so much.
Yes,
Over
thank
to
you. Thank you.
Okay. Yeah, thank you, Deepji, for a very interesting talk and triggering the attendees basically to ask the question, and they will be interacting with you. And then so thank you very much.
Yeah, thank you.
We have another speaker in this session from academia now, Dr. Gaurav Trivedi. Gaurav Trivedi is associate professor at IIT Guwahati, and he's from Department of Electronics and Electrical Engineering in IIT Guwahati, and he worked as a senior member of technical staff with Cadence Design System and Berkeley Design Automation, and presently mentor Siemens for 3 years, and as a postdoctoral fellow for 2 years at IIT Mumbai before joining to IIT Guwahati as a faculty member. And he did his doctorate from IIT Mumbai and master's in microelectronics from IIT Mumbai itself. His current area of interest are circuit simulation, which includes analog, RF and digital, and VLSI CAD, electronic system design, computer architecture, semiconductor devices, hardware security, embedded system, and IoT, high performance computing, and large scale optimization, of course, machine learning, very, very important areas he's working on. So with this, I request Dr. Gaurav Trivedi to please, share your screen and start your presentation. Thank you very much for accepting our invitation.
Am I audible?
Yeah, you are audible, sir. Yeah.
Okay. Thank you. Is my slides or are my slides visible?
Yeah, it is visible. Just make it full screen. Yeah.
Yeah. Okay. Thank you.
Yeah.
So since this particular thanks for the invitation, Professor Srivastava. I'm to say this is. I've tried my best to come up with some. I just bridge some of my thoughts in the form of a slide, because this particular workshop is in the theme of the fabless ecosystem in Madhya Pradesh. So specifically, last so many years, what is my observation, and what and why we should actually go for the fabless ecosystem, in fact more aggressively on the chip design fabrication complete facility in the Madhya Pradesh, which is the need of the hour. So that's why actually my particular this talk is very much focused about the EHDM manufacturing for Atmanirbhar Bharat. Why is it required, and what are the shortcomings and all? Okay. So when we just see precisely, right, we have everything you can say electronics nowadays. Okay, except the cutlery and the utensils, I just say on the lighter side. But if you just look at it, we have a lot of electronics around us. Okay, without electronics, nothing. No system actually is acceptable to us. Just a moment. Yeah. So this is all we know about it, right? When we talk about the electronic industry precisely, there are some data actually which actually I presented to Niti Aayog long time back. So you can say I got that data and club it here as well, because this is something like this we must know precisely. Okay. When actually we say why we need VLSI design, manufacturing and all. Okay, and we have some you can say idea about it. So here actually I'm presenting the actual numbers, why we should go for these kind of things and why. So this is precisely you can say if you just look at electronic system industries overview, so we have the consumer electronics, IT, you can say industrial electronics, strategic sector, okay, solar, medical. There are so many things out there. Okay. So when we talk about the Indian hardware production, it is only the 1.3% of the global production till date. Okay, so That is why precisely this is really one of the most important part. We must know that our own existence in terms of the design, okay, is good, okay, but not for the system which actually we are making in India for India. I will say I'm very much talking about the indigenous system which actually we own completely. Okay, if you just look at the different product-wise revenue, the mobile phone, which has now the highest penetration, and that is why there used to be the big sales. So on the many e-commerce platforms are there, the televisions, so laptops, computers, accessories, and there are so many things out there. If you just look at it, this is just the you can say the segmentation of where we stand. Okay, in terms of the top 10 product by the revenue. When we talk about the India ESDM market survey, precisely if we just have to look at it, what is in the export, how much we are doing, now how much production in the revenues we are gathering and all. So the production, when we talk about the revenue side, it is $32.7 billion is there. Which actually, if you just look at the table below, the consumer electronics, electronic components, industrial electronics, hardware, communication and broadcast equipment, and the strategic electronics, they turn out to be the 32.7 billion, and the total, they cover the total 100% in the Indian ecosystem. Okay, so when we just look at as an example, I have just taken an example from 2010 to 2015, which actually indicates the import-export scenario. Okay, so when we talk, you can see precisely that from the 2010 to 2015, the revenue actually grows in terms of billions of dollars from approximately $60 billion to approximately $95 billion or so. Okay, so based on that, we have actually forecasted a lot of things, including becoming a $400 billion economy in terms of the electronic market and so on. But that could not be realized so soon, and for that actually we really have to make a lot of efforts. So when we talk about the international scenario, so specifically of the ESDM, so if we have to compare ourselves, we have to see what is our total market capitalization as per the electronic systems in general. What is the total revenues collection? Okay, what are the present capabilities worldwide? Okay, which other you can say countries have, which we do not have. Where we do stand in this particular area, what are the reasons for the lagging, and why should we go for the leapfrogging. So here specifically, the last point is very much important for me. Now there is a Government of India initiative on the India microprocessor design, which is I find it's very important one. Okay, but started in approximately in 2016, I believe. Okay, now 5 years down the line, still we do not have any working laptop. I would say, if you ask me a processor, I want a full processor. Okay, I want a full processor which is working. Okay, at least in the form of a desktop. At least I can use it in a desktop. Okay, a Windows 2000, Windows you can say 2007 or Windows 2008 or the recent you can say the Windows version must be running, recent Linux version must be running. I want that great microprocessor. Okay, if that is my personal choice. Okay, by the way, so if so that is there, but where are we after 5 years? Still we have designed a few IPs. Okay, and we are saying that these IPs will be very much required for the IoTs. Fine, but IoTs, the segment is totally different. Okay, and the game also is totally different. So again, we have to, you can say formalize our strategies, and we have to work accordingly. But why leapfrogging? Because why I'm emphasizing quite a lot on this, that is just because we have in my opinion, this is my personal opinion, I'm reiterating. Okay, we have lost you can say the war of microprocessors. Okay, unless there is a good funding is there and the industries are involved, okay, properly, we cannot actually have a respectable position. And I will give an example for this as well. Okay, so now the future technologies. Okay, where we are still depending on the foreign companies. Okay, 5G, 6G, maybe even the terahertz. Okay, or maybe the quantum computing. Okay, there are so many, you can say, niche technologies are there. So in that area, if we start now aggressively with a very good funding, okay, then we actually can have edge over the people in future, and maybe the future can be brighter than today. Okay, so when we talk about the current scenario worldwide, I'm to say if we just look at the segment-wise funding, okay, so most of the, you can say, product in the area of computer vision, AI, speech technology, edge computing, they were funded heavily by the investors. In 2018, okay, which was the, you can say, one of the most productive year in terms of the funding after the dot-com bubble burst, when the $3 billion of funding was given by the investors for the fabless companies. Okay, how much has come to India? That's a big question. Okay, so and Chinese government, if you just compare the China, okay, their funding, actually they have increased their funding. Whatever the funding they have, base funding they have provided to their startups and the companies by more than 100% as compared to 2014. Many domains come. Okay, neuromorphic computing people are talking about, quantum people are talking about, Elon Musk is talking about the domain specific architectures or the specific processors. Okay, and the computer paradigm is shifting. And now one more shift is there precisely. Earlier, Intel, AMD, TI, these companies used to be there, which used to do the VLSI design. Okay, Toshiba, Sony, these are among those as well. Fujitsu. But now the Google, Amazon, Facebook, Twitter, JP Morgan, and Chase, they have also started VLSI design. So the VLSI design precisely has, you can say, has increased actually. I'm just saying it has penetrated other segments as well, and people have realized the need for the VLSI in almost every segment. Okay, whether they are having their own data centers or they are having their own social, you can say, security, so social networking sites are there, and all they are very much. So they are precisely very much focusing on that. So and especially, and the second thing which we have recently watched that. The race to the space, right? So the space has become the next frontier. SpaceX, NASA, ISRO, okay, all we are precisely going to beat each other. And in fact, China is also there. They are having their own. The Sky Lab is there, okay, and maybe India soon launch its own Sky Lab, and the who will set up the first base on Moon, or you can say the Mars or so. And there are many, you can say, benefits are there. I don't think that we will be occupying this particular planet for just for staying out there. Okay, tourism can be one of the thing, but most of the, you can say, focus is on the rare earth materials, minerals. Okay, gold, maybe diamonds, and which has to be, have to, you can say, dig, and you have to bring it out here. So this is precisely the growth rate of the India with respect to the international ESDM. You can see the relative change precisely how this world is moving, and how the India is moving precisely is more or less on the on the same side precisely. So we are not doing bad here. Okay, in fact, the focus on India by many governments and the many companies is increasing. Okay. But when we talk about the ESDM revenue, you can the perspective, the product size and the service size, service industry size is there. So you can see that specifically the product size industries, they are growing, and the service industries are also growing. Okay, there are many companies actually they have started, you can say, manufacturing there, or I just say the assembling their products in India, and now they are precisely they are actually now they are you can say exporting that product to rest of the world. When we talk about the electronics market in India in terms of the the high value and the low value, you can say, manufacturing. This is a very interesting one. Recently, I was working for. Recently we are working for some initiative which will be announced by IIT Guwahati soon in association with one of the IIT Roorkee and one of the other organization. So they are specifically this we are doing something. We propose something to Ministry of Skills for. I'm going to say for, you can say, digitizing the India and all. So one initiative we are starting, so with Research for Resurgence Foundation. Nagpur, and so I'm talking about that. And so when I was formulating that particular proposal and writing the vision document, I came across this data. This is really very interesting. If you just look at it, the high value added, you can say products are, I would say, if you look at it, the 4.12 to 4.35. Okay, and it has reached up to that only, right? Okay, the total, I'm to say percentage wise or so this is coming like this. Okay, but sorry, this I'm to say there is not much increase is there. But when we talk about the low and the medium added value products are there, they have increased from the 10.5 to 18.3. So this is you can say $1 billion, so which is approximately close to the double. Okay, and this is precisely this is very interesting. Okay, so what we have also targeted, if you start making, you can say, the mouse. Okay, if you start making, you can say, digital thermometers or the daily utilities which are not very costly, which is cheap. Okay, we really can save a lot of money. Okay, we can provide a lot of employment to the people locally. Okay, and that thing will be perfectly Swadeshi. We can call it the 100% Swadeshi. Okay, so the Swadeshi manufacturing actually we can start. I still remember Swadeshi, what I heard when I in the book of history, when the Swadeshi movement was there during the struggle of independence. But I think here also we have to again go for another Swadeshi movement in the area of ESDM. Okay, and many, you can say, computer related products, many the computer software related products. Okay, so and the focus, instead of having the high value added product, you can say products, I think if we focus currently in order to, you can say, to place our feet firmly on the, you can say, low and the medium value added products, then that will really be great. So if we just see the semiconductor design industry growth, okay, which is composed of the VLSI design, embedded software, board or the hardware level design, you can see the software market is anyways growing. Okay, we know all about it, but the board or the hardware level design and the VLSI design also is growing substantially. Okay, it has this is a little bit older data because the few things precisely were not available. So but this is a right indicator, and this is increasing even in the today's scenario as well. And so this particularly, I'm to say, we are doing really a huge amount of, you can say, design in India. Okay, mostly not for India, but for the offshore companies also. Okay, and things which are designing here, okay, coming back to us, okay, through another channel, okay, with a different tag and with a different price tag also. So the India's contribution on the GDP, in the India's ESDM impact on the GDP is, if you just consider it, the least among the Taiwan, South Korea, and China. Okay, so this precisely is there. Okay, and if you just look at the region, I will talk a lot, but in the end, little, and it's towards the end precisely. But this is really very sad. So when I was writing one of the, you can say, during the presentation long time to the Niti Aayog, when I was presenting this data to them, and I just took the data from the reports published by MIT or the ISA, okay, and many other organizations. Actually, I took it from them only. Okay, so when I first looked at this graph, it was in a report. So I found where is India? So there was only one China graph is given me here. So then I found, oh, India precisely is nothing here. So if you just look at it, I mean, say this is between the 92 to 2014 is there. 92 we were more or less same. Okay, but our policies and their policy made a huge difference. We are still at the same place. Okay, and they are leading the world in the area of ESDM. Okay, so if we have to precisely beat them, okay, this is 2014, but now they are close to $400 billion. Okay, whatever is showing precisely it again increased. Okay, so now if we have to really you can say beat them, we have to, you can say, make a jump. Okay, a quanta should be something like we have to surpass. We have to, you can say, generate revenue so that the $400 billion can actually be generated per year. Okay, a worth of revenue. So why we are behind? Okay, there are many factors out there, but one thing precisely is the taxation. Okay, government has eased up pretty much a lot. Okay, but there are another problem is there. There is a non-ability to the compounds domestically. Okay, so if we have to buy single diode, or maybe if we have to buy certain chips, okay, basic level, even those chips are not being manufactured in the country. We have to buy, okay, these chips are manufactured by somewhere in Taiwan, China, Philippines, Malaysia, and some other, you can say, offshore facilities, and we procure it from them. Okay, and if we have to set up if you have to, you can say, set up a particular, you can say, hub or the house, we have to precisely incur a lot of cost. VLSI design tools precisely, right? I have to say, if I have to buy for the commercial thing, so one license will cost me in 5 crores to 6 crores. Okay, so who will give me just 5 crores or 6 crores? So that is there. And higher manufacturing cost due to the infrastructure issues are also there. Where to set up? If I set up a shop in Bangalore, okay, then I have to pay the higher infrastructure cost. Although nowadays there are many good options are available, but these are not sufficient. Okay, and that actually all adds to the higher cost of the design. Okay, and if I just send, you can say, add to the incidentals like the COVID or so, the cost becomes too high. Okay, so the price of the domestically manufactured product precisely, you can say, rises like anything. So this actually we have to address. But the good part is that the WTC said that the world semiconductor market will grow to 2018 by $388 billion. Okay, and that is the largest growth year since 2010 is there. And we were very much expecting that we will go up to, you can, $400 billion in this particular by 2020 or so, but we could not reach it here. And so we have you can say we have increased, you can say, that this particular timeline by the 5 more years. Okay, I think due to Corona this will again be increased. Okay, but specifically if we reach $400 billion, then the ESDM imports will exceed the oil import, and this will become one of the prime, and it is still the prime area, and in fact it is the prime the sector to, you can, focus on. Okay, so but if we just see, I'm to say we can, if this happens precisely, okay, we will be able to, you can say, give a job to 27.8 million people, which is approximately 2.8 crore people in the country. And if I just go with the earlier planning commission report, so one job, okay, one, you can say, blue collar job impact actually 50 people. So if this is so, then the India can actually be considered as the developed country, because we can impact that many number of people. So hope so it becomes a reality. When we talk about the semiconductor design market in the India, this actually, you can say that I'm focusing only on the design part because this is all about the ESDM, but chip design part, the $14.5 billion, okay, it was expected to reach up to $52.58 billion in by 2020. Even during the Corona, but I found that there were many people actually have got the jobs, okay, and they have started work from home, and the new culture has emerged. So I don't know the number, but this number seems to be very large, but definitely much more than 14.5 we might have reached till date. So there are precisely when you talk about the so this up to this precisely we are talking about why we are actually very much where do we stand, what is precisely our position, okay, with respect to the global scenarios are there, okay, and so on, okay, and why should actually we go further, because this graph itself is an indicator, okay, and a good motivator as well, okay. So ultimately the need for the leapfrog growth is precisely when we are focusing, right? Simply I will just say, okay, I will just share actually my own in fact there are things which these things also is known to you as well. In this particular arena, I'm to say what we're talking about, there is no single product there which does not contain any, you can say, electronics, okay. Approximately everything is connected with the electronics. Now we are talking about the wearables. Google is coming up with the Google watches with more and more features. Okay, more and more health aware, you can say, features are there. Okay, So people are coming up with all those things, right? So electronics, or you can say I just say the miniaturized electronics with nothing but the VLSI become the integral part of everything. Okay, so if we do not become self-reliant or Atmanirbhar in this area, okay, we will have to depend on foreign technology forever. Okay, and this may cost us dearly because we don't know what is there inside. Okay, because the technology has become so much complex, somebody, you can say, insert a hardware trojan or a hardware bug in a chip. Okay, right? I cannot find it out. This is not the software, and the finding of that is it's not very easy as well. Almost next to very impossible. Although there are many ways out there, okay, but it is actually next to the impossible is there. Okay, so this is precisely I'm to say one of my if you just ask me, this is precisely my vision is there. Okay, zero foreign dependency should be there. Okay, so this is there. So what are our initiatives? Our initiatives, I will quickly go over this. Mighty actually, which were Mighty, which were earlier, Mighty actually, Mighty, which were earlier, Mighty supported a lot of, you can say, programs. VLSI Design Centers, SMDP project, India Microprocessor Program. Okay, right? They have set up, you can say, FABC in Hyderabad. Okay, one of the center we have also proposed at IIT Guwahati in this domain as well. The Safal Entrepreneur Park in Delhi, in Bhubaneswar. Okay, the state government initiatives like the Tea Hub in Telangana, Makers Village in Kerala, all those things precisely have been initiated by the central government and the state government. Okay, so this precisely is there. But if when we are doing this thing, somebody asks me, is it sufficient? Okay, I doubt actually. Okay, so there are 23 IITs. Okay, there are approximately 25 NITs. Okay, but let's say if I just club all the triple ITs or the top tier institutions in India, okay, where the VLSI program is running, okay, there are not more than 100 because the organizations are there. Okay, out of these 100, you can say institutes. Okay, every year on an average 20 MTech students graduate in VLSI. This is an average number, right? So this turned out to be 2000. Okay, and if I just club everything, let's say the 500 PhD students are also okay getting graduated on an average from per institute. So are these 2,500 students okay who have become the experts in this particular area are good enough okay to drive or to change the particular scenario? The answer is no. So whatever we have done, okay, this is fine. This is absolutely required. But at the same point of time, okay, many more you can say unorthodox and the unconventional methods are required, or the ways are required to boost the production. Okay, so hope so. IT Guwahati will be able to do so. You can say justice in this particular area in coming time. For the semiconductor Chandigarh, when we SCO Chandigarh, when we talk about so we are having one fab in India, and like my earlier my friend Mr. Deep was very much you can say discussing on that. He has already discussed about the SCO Chandigarh, the facilities and all. IIT Guwahati is the first institute in the India who drew the MOU with SCO Chandigarh, and it was initiated by my own efforts. Okay, at that time, after that, every other IIT and many institutes in the country they started forming it. But it is good. I proudly say. Okay, so ultimately, when we talk about the SCO Chandigarh, my interaction with them is really good till date. They are, they have a good, precisely, you can say, ecosystem there for 180nm design technology. Okay, they have designed, you can say, a fabricated 4 MB SOM with a 5 million transistors here in India itself. Although it looks like pretty low with respect to the other countries, but yes, in fact, this is actually a good motivation for us to, to grow this particular facility. And what we actually have to do here, we have to, because this particular fabrication unit is very much underutilized, so we have to, you can say, keep it running. We have to generate the demand, and unless the demand is generated precisely, okay, to say there will not be any good, you can say, increase in the facility will be there. So this precisely was not very much needed actually, but I just put it up because we are having only the SPL Chandigarh, which is very much helping academia and the India's strategic sector to design chips and all. Okay, but at the same time, what I feel, this is again I'm saying my opinion only, is to, if we really have to strengthen this, then it should actually be you can say spinned off as a commercial entity, which it was earlier. Okay, in the same flavor and with new policies, very good funding. Okay, and with the set goal that they have to, you can say, develop the expertise in the area of fabrication. Okay, because setting up the fab in India, okay, it's a big challenge. Okay, out of 2,500 people, okay, which actually I say is a very good number. Okay, okay, if we really have to set up a fab or you can say big design houses in the country, okay, I would say we are not having enough, you can say, experts or the manpower. Okay, so whatever the you can expertise we have, if we just grow this, okay, beyond a certain point, then that will really help us. So the ESDM growth, okay, right. So this is precisely when we see, we have designed one microprocessor. It's a very good initiative. It's a made in India 100% Swadeshi, Shakti, Vega, and Ajit. Sorry, I'm just my problem is that I E actually not R. Okay, so the Shakti, Vega, and Ajit we have designed. Okay, and okay, Shakti, Vega, and Ajit we have designed 100% Swadeshi microprocessors are there. But are there anything else which actually we can use, right? Most of the Indian MNCs, they are just providing the services. They don't have the confidence in Indian academia. Okay, they are not into the product design. Okay, right. There are no Indian EDA tools. We are very much depending on the Cadence, Synopsys, Mentor Graphics, and few other EDA companies. Okay, to provide the tools to us. Okay, what if there are some sanctions imposed, no US made technology will be made available to India? Then what will we do? Right? And if we really have to go for the procurement of this, the cost precisely is 5 crore per bundle minimum. And that is how I'm talking about one tool, one license, or maybe the one bundle. So that precisely is there. So a startup, who will begin the startup? We can have the Flipkart, we can have Myntra, we can have many other Indian startups are there. We can have Ola, right? Because the capital is not that much required and the funding is very much easily available. Okay, so there is no trust factor is there on the Indian innovators and the people out here. So that is why I'm to say, so government will have to really boost this activity with a huge funding. You say how much? I say I'm in the tune of $2 to $5 billion, no less than that. If government will not aggressively fund the startups, okay, and mentor them properly, right from the product concept to the product design, and then taking it to the market is there, India will not become Atmanirbhar. Some startup India program is there, okay, fine, okay, some people are connected, some people are getting, but that is not enough. That precisely is my own, you can say, assessment is there. There are, you can say, various ESDM initiative government has taken, but you can see something is there, something is not there. We have also proposed, if it comes, then it will having all the components there. We have also proposed the 100-level hardware and the software project through this center. Let's see if we are able to successfully, you can say, go with this, right? So when we talk about, I'm going to say, what is the motivation? Why? Okay, fine, this is there, that the company with China is actually very much motivating to me. Okay. But can we do this? And the answer is that yes, we can do this. In US, actually, when sanctioned, you can say you impose some sanctions after our new testing. Okay, at the time of late Shri Atal Bihari Vajpayee tenure. Okay, at that time precisely, what to say, our RR-CAT, which was in Indore, okay, was very much, you can say, had to bear the impact. Okay, but finally we have come up with our own helium in the gallium arsenide laser, and today industry lasers particularly, and we are at par in this. Okay, so this is a blessing in disguise. Second thing, it's not from India, but India's friend Japan. Japan, precisely, this is something they have done. Japan, I would say, a lot earlier realized that this is going to be a big, I would say, dependency, or you can say the monopoly in the area of processors. So they have, you can say, come up with their own K computer. So Japan Ministry of the Education, Culture, Sports, Science and Technology, they have, you can say, contacted Fujitsu, Hitachi and NEC to design its own, you can say, microprocessor. Hitachi and NEC dropped, but Fujitsu come up with its own UK processor. And in 4 year time down the line, they have not only come up with their own processor, they designed the K computer. Okay, and they designed in 2010 a supercomputer based on their K processor, which was the fastest supercomputer. Since 2010 till 2018, okay, or till 2020, I think, in last 10 years, this computer was in the worst top 10 fastest supercomputer. And again, they came with the same technology. Now they are claiming that they are one of the universities or center. They are having world's fastest supercomputer based on their own K processor. They have done it. They started in 2006. And 2010, they were having the computer. Not only the computer, they were having a supercomputer ready by that time. Forget the microprocessor. So this is something which we have to do. This is such an inspiring, you can say, story of the K processor and the K computer and the supercomputer based on this, that India must just follow this, and which requires a good involvement of the industry and a very good funding by the government. The target based, right? So, and with this, we require multiple national-wide centers should be there. So these centers precisely should be there, like, for example, let's say IIIT Guwahati is hosting this. IIIT Guwahati is, you can say, excelled in this one particular area. So if a center, national center in that particular area must be erected in Gwalior, IIIT Gwalior, IIT Guwahati, IIT Bombay, wherever we are having expertise, we should have, okay, our respective centers are there. There should not be, okay, the concentration of all the technology to one place. There should be, and a proper industry level interaction should be there, which should not be, you can say, transactional. That some guy is coming, okay, selling the product and running away. No, the people must come, okay, for the collaboration, right? Okay, and so this part precisely is very much required. This is, I quickly go that if we just look at the target areas of, I was saying that we have to precisely target a lot of things also. So my own precisely, if we start doing this, so with the automobiles, the mechatronics, railways, aerospace, so many areas precisely we actually can impact. In order to do this, what are the facilities needed to us? Okay, so we need the centralized prefab and verification facilities. We need the centralized post-fab testing in the characterization facilities, and these facilities must not be under the, you can say, the under the umbrella of any academic institute. Okay, these should be the direct, you can say, facilities which must be, you can say, directly under the you can say the banner or the umbrella of certain ministries also. Okay, it should have everything. Those who want to do this, they can just go utilize this. Okay, the facilities, do the design, and then they can go out. State of the art PCB design fab facility. Okay, we do not have it. Okay, if we have to go for the PCB design, if I have to go for the 24-layer PCB design, where should I go in India? I don't know. Okay, we need to standardize the design flow. So there is a lot of effort should be done, and STL Chandigarh should actually make the frontier in this. Large electronic system design capabilities. We should have the proper ecosystem where actually we can test a 1 GB or a gate design. Okay, sorry, 1 billion gate design with a large number of memory. So these kind of things should be there, and a proper connect with the startup India should be there. Okay, there should not be any confusion also. Okay, so that way it will really impact. Okay, so unless the state of the art facilities are there, unless the good funding is there, we cannot expect a good to come out of this. Can we do this? The next question is this: if suppose government provides everything, so my answer is that yes, we can very much do this. Okay, not only we should do this, we also should look for some other parts of the, you can say, expansion as well. So smartphone came, we adapted, and we actually learned how to do the app design. And India actually is doing. India is one of the largest hub of the app design in the world. We learned it. Okay, so we know. Okay, so we know how to build the technology, how to manufacture it, and how to become the self-sustainable. So we know how to learn and how to adapt and how to, you can say, react after that. Okay, so many you can say industries actually, sorry, many countries actually have done this. So the first step which our honorable Prime Minister Shri Narendra Modi ji has taken, and there was a Make in India event in 2016, if I could remember, 5 years back. That was really the need of the hour. Okay, so specifically, I'm going to say we have to start doing the manufacturing in the country. Okay, once the manufacturing will be there, okay, then we actually have to go. Then actually we have to go with once the manufacturing is done, then we have to go with you can say start manufacturing the devices, the components. Okay, and once it is there, then you can say people can come. Initially, I mean, from 1 to 1 and 3. If we just talk, if I just talk about, this is all about doing just assembling and, you can say, the manufacturing part. Okay, which many companies are doing. Dell is doing, Samsung is doing. Okay, HP is doing. There are many companies who started doing. Apple has started doing through Foxconn in Bangalore. Okay, you might have heard there was a strike in COVID times. Okay, and which was, again, I just say, unfortunately, was China funded. Okay, so but specifically once this thing start happening in bulk, then the IC fabrication facilities will start happening in India. Okay, because there is a demand, so there is a proper mean to, you can say, set up the entities for the supply. Okay, so this actually will, you can say, this is the only way, okay, to, you can say, set up, okay, a complete ESDM ecosystem in the country. But for this, before we begin this, we need adequate manpower. Without having adequate manpower, nothing can be done. Okay, so upskilling is one of the most important part. Okay, and upskilling, okay, should be in such a way that people learn the things, okay, and they enjoy learning, as they enjoy learning playing. Okay, so new policy in education might be very much beneficial. I hope so, because it addresses a lot of good things.
I'm sorry, Dr.
Okay.
Trivedi.
So
may I request to please just wind up, because other speaker is in queue.
Yeah, so give me only for 2 minutes. I'm just winding it up.
Yeah, please.
Okay.
Yeah.
So there are many, you can say, steps for the leapfrogging is there. So I skip this part because more or less actually I have said it. So, okay. So, but the target beneficiaries precisely here will be our faculties, students, startups, research labs, and the people of the country. So not only this, I'm not talking about the, you can say, the chip design fabrication. One of the most important part precisely is the, you can say, fabricating, or you can say the growth of the wafers. Okay, so you can say, or the manufacturing of wafers. So Brahmaputra science, for example, is one of the most this actually study we have provided to government of Assam and government of India as well from IIT Guwahati side. Okay, so here actually we can use this particular strand, okay, to, you can say, manufacture wafers and to extract some rare earth materials as well. Okay, so ultimately, if you have to summarize, we have precisely have to build an ideal for the ultimately the ESDM activities in India. We have to you can say build a proper ecosystem which involves academia, industry, and the nascent startups. Okay, we should have the proper funding. Okay, free access to the tools, a national repository of the IPs or so. Okay, and a very good seed funding to the startups in the tune to 5 to 10 crores with all the facilities. Okay, only then the change will be there, and the true made in India product consumption, and only true made in India or product development will happen for the Atmanirbhar Bharat, and which requires other change in policies also. Thank you.
Thank you, Dr. Trivedi, for enlightening us on various activities you people are involved in, and especially in the electronic system design and manufacturing, and what are the challenges and opportunities in moving or marching towards achieving the goal of Atmanirbhar Bharat. And I'm sure that the participant or attendees must have got enlightened with your talk. And because we are having a shortage of time, so I'm not asking for the question. So they may ask the question directly in the chat box, directly to you. Thank you so much for your talk and accepting our invitation for this particular session.
Thank you. Thank you, Professor Shiva.
Thank you so much. So may I move on
So
to...
I'm logging off. I'm logging off from this. If there are any queries are there, I request people to directly write me an email. Thank you.
Thank you so much. Thank you so much. Thank you so much. So we have with us next speaker, Dr. Jawar Singh. And Dr. Jawar Singh is at IIT Patna, is associate professor. And he's again from electrical engineering and electrical engineering department. He is Dean, Associate Dean, Research and Development at IIT Patna. And Dr. Singh is currently serving as Director of IIT Patna Vishleshan iHub and Foundation for Innovators in Science and Technology. Very, very important domain he's looking after right now, the innovation and startup activities. So both are, as he said, that Section 8 companies. He received his doctoral degree from Department of Computer Science and Engineering, University of Bristol, UK. He obtained his master's degree from Department of Electrical Engineering, IIT Roorkee, and his research interest includes devices and circuits for neuromorphic computing, and the area I think he's going to talk about today, lower power integrated circuits, embedded system, hardware security, RF energy harvesting, and he also holds 2 US patents related to computer semiconductor memories and recipients of prestigious Indo-US Fellowship 2016. And he has more than 40 international journal publication, 50 conference publication. He has written book chapters and full book from Springer, Germany, and he has been to various places in abroad as a visiting researcher, like University of Pennsylvania, USA in 2009, then North Texas, USA, each for 6 months. And he's also been a member of IEEE, editor of IT Technical Review, and served as associated in many achievements he has to his record. So with this, I invite Dr. Jawar Singh for his talk in this particular session. Dr. Singh, over to you, please.
Yes, so thank you, Dr. Anurag, for detailed introduction, and you finally managed to fetch my... I'm audible, am I right?
Yes, you are audible. Yeah,
all right, thank you very much. So firstly, I thank all the organizers and the dignitaries virtually connected. Dear participants, I'm Jawar Singh, has already been introduced in detail. So without taking too much time, because we have another program in line. So moving to this, I'm just going to talk about the neuromorphic computing chips for next generation AI. The neuromorphic computing, basically, if you see, are the cross points or the crossroad of neuroscience, computer science, and electrical engineering. It encompasses the study and design of a bio-inspired system. So in this talk, I'm going to talk about the latest development in this neuromorphic computing chip designs. And my current research is also in this domain. Basically, we are working towards developing some models. They can be used and exploited for neuromorphic chips. This gate is our Indian Institute of Technology, Patna's gate 1, actually, at the background. So moving to this, one of the important aspects with these machines nowadays is the man versus machine channel, which is a very common competitions we have seen actually in the past. So if you look at it, the very first in 1997, this IBM Deep Blue versus Kasparov, and then later on in the IBM Watson versus Canbrad 2011, and then recently the Google AlphaGo, one of the complex game versus the Lee et al. So what is the common thing and why I'm putting over here, the more important aspect here is this one actually. So if you see, these machines involves a huge amount of power to beat with this human brain. And so in case of the IBM Deep Blue, it is somewhere it takes around 15 kilowatt of power to beat a very small human brain, which just consumes around 20 watt of power. Similarly, this another the IBM Watson, which consumes around 200 kilowatt power, a huge amount of power if you see. And the latest one is the Google AlphaGo, which is Lee et al. in which the deep algorithms were designed to play this game, and this consumes around 300 kilowatt of power. So now the question arises, where is, if you see this human brain is very small and it just have 20 watt of approximate 20 watt of power consumption, and even though this computer takes huge amount of power to beat this actually. So therefore, nowadays people are moving basically from these traditional computers to some brain-inspired computing. That is the main motivation, and because there are huge power footprint actually involved. If you see, they requires a huge amount of power. So can we make our computers? They can perform, or their computations are inspired from the human brain computations capability actually. And the term this neuromorphic computing was coined in late 1980s by a Carver Mead actually, and who thought that there is a very direct relationship with the computation in the human brain biological channels and the transistor that we use, MOS transistors. So if we operate these MOS transistors in a subthreshold regime, then the flow of ions is having a quite good emulation with the flow of ions in the human brain actually. So he thought of this, and lots of research is going on in this direction actually. So moving towards this another set of the motivation, if you see in the past few years, we have been seeing there is a lots of most of the computers, if you see, are somewhere here around, and they are ticking with a clock frequency of few gigahertz actually. If you see, that clock frequency is just few gigahertz. So in last, if you see in last, we can say almost in 20 years, this clock frequency is almost stagnated actually. So for example, this Pentium 4 series processor, which was almost in 2000 at the end, 2000 or 1995, 2000, and since then, if you see, all the state-of-the-art processors are having operating a clock frequency is somewhere 2 to 5 gigahertz. There is no great change in this clock speed. And the reason can also be correlated with this power density actually, power density. So the power density comes around somewhere 100 watt per centimeter square. So this is one of the limiting factor of why we are not moving, or why the clock frequency is not increasing actually. And if you look at the backward size actually, if you see this brain, human brain, which sticks at a very low frequency, just few hertz, and the power density is also very small. So now lots of research and lots of work is going on in this area, so that the chips can be based on this. And firstly, if we look at some of the conventional von Neumann processor architectures, because virtually all machines today, we have the architecture which is a von Neumann computing architecture, virtually in all machines actually. So in this architecture, they are rely heavily on separate processing as well as the memory unit actually. If you see in all these conventional computing approach, parallel computing, and then the latest the new computing paradigm, if you see over here actually. So the thing is that in these von Neumann computing architectures, the processors they are separated, the memory and the processors are separated, while in the brain organization, or the brain organization principle rely on a distributed computing, or the memory and the processing elements are co-located, and it performs basically within the neurons and the synapses. These are the basic element actually. So most of the chips that I'm going to talk about based on these neuromorphic computing in this line. So this is one of the latest development from this Intel actually. Intel's Lehoy I'm going to talk about in detail basically. For more details, you can also visit this. So this is the latest outcome from this Intel actually. So if we just put these two aspects together and then we compare, then we can see that the human brain and the Blue Gene supercomputer. So the human brain is usually having a neurons of the order of 10 raised to the power, 10 raised to the power 11 neurons, and it just operates few hertz. And there are almost 10 raised to the 15 synapses, and the power is very small. Similarly, we do the same thing if we compare with this von Neumann computing architecture. And in this Blue Gene computer, basically, specifically in this Blue Gene supercomputer, and it was used for simulation of this mouse cortex. And for simulation of this mouse cortex, they use almost 8 into 10 raised to the power 4 neurons, and the clock speed was somewhere around 1 gigahertz, and the power required was too high actually. So you can imagine, just for a smaller, just to simulate this activity, the power consumption is too high. And one of the major reason, if you compare basically this human brain with this traditional computing system, is that actually in most of the computers, as I mentioned, the von Neumann computing architectures, in which the memory and the CPU as well as the IO devices, they are separated to each other. So there is a huge influx of the data takes place between these elements, and that consumes significant amount of energy, as well as it put lots of or it is a bottleneck of throughput basically, or the performance. And so in this direction, there are lots of recent development. Particularly, we look at this IBM's True North chip. I'm going to talk about in detail, and there are two more important chips. One is Leohui 1 and another is the Leohui 2 from Intel. And before we move towards these two important examples I'm going to show you, I'm just going to talk about little about the economics of this chip design actually, because this program is more towards this chip design and development. So if you look at this, the economics of the chip design, the benefit of making things smaller have been almost lost actually, we see from this diagram. Specifically when we have moved from beyond 28 nanometer. So in this diagram, I'm just, this slide shows you the number of transistors one can buy in $1 actually. How many transistors one can buy in $1? The number and the length of transistor watt per dollar. So if you see in 2002, the technology is 180 nanometer. So one can buy 2.6 million transistor in $1. But as we increase, as we move on, like let's say in 2004, 2006, or let's say in 2008, the number of transistors I can buy is 11.2 million in just $1. So you see it is quite good actually, because I'm getting more number of transistor in the same dollar. But if we reach at this level actually, this 20 nanometers somewhere, sorry, this 2012 and 2014, and the technology is, if we move from 28 nanometer to 20 nanometer, then the cost is not reduced actually. So here also I'm getting 20 million transistors in $1. Here also I'm getting 20 million transistors in $1. And it goes worse basically if we move further. So that is how basically these compaction or this miniaturization is no more giving the fruit in terms of cost of per transistor actually. Similarly, there is another trend I would like to share is in terms of the consolidation of this fab. CMOS fab basically. So if we look at some of the latest or some of the important fabs across the world, then we can see there is a huge consolidation or merger or acquisition from last 20 years. So in 2001, there are around 15 to 20 popular and famous fabs. But now in 2015, even there is a recent merger. You can see the IBM has merged business with the Global Foundry. So there's a lot of merger and acquisition is taking place. So it shows that this fab business is, I think, I don't know whether it is profitable or not profitable, but the trend shows that a lot of companies are merging their business or they are aligning their business in different domains. So this is the one takeaway we can have actually if we are going towards in this direction. So in this direction, I'm going to show you about two chips basically, as I mentioned. One is the IBM's True North actually. So this is the IBM's True North. If you see the architecture of the IBM's True North chip, this chip uses the brain-inspired computing or a neuromorphic chip. Its efficiency is remarkable and it is close to the human brain efficiency. So if we give some numbers or if we see the arrangement and organization of this chip, so this is the smallest, basically here we have is one core, let's say, and the integral and other parts. So here they have used this neurons and the synapse, and rather than using these zeros and one, they have used a kind of a spikes actually. So the information is coded in the form of spikes, and they've used different kind of neuron model actually. Generally most popular neural model is LIF neuron actually, and in the synapse they have used a static RAM actually. So if we compare in terms of some important numbers, so the chip that is the True North is comprised of 5.4 billion transistors, and the area is somewhere around 4.3 centimeters square. It is based on Samsung's 28 nanometer process technology, and it consumes 70 milliwatt of power for performing a very simple task, specifically for recognizing some characters or image processing. And here, another important aspect I would like to highlight, this True North has 4096 cores and each having 1.2 million transistors. There are 265 neurons in each core. So you can see that the designing a single neuron require approximately 10,000 transistors. So if we can develop some model basically where the number of transistors can be reduced significantly, then the efficiency and efficacy of these designs can also be further improved. And some of the salient features, as I mentioned in the previous slide, so these are also the same salient features you can see here. So the True North chip uses digital neurons. So there are digital neurons and the digital synapses actually. The digital synapse is made of 8 transistor SRAM cell. So because the 8 transistor SRAM cell has certain interesting features, for example, it is having a separate read and write ports, so it allow easy access of transfer of the data as well as the throughput. Similarly, this True North chip was demonstrated with 70 milliwatt of power consumption, having the real-time object recognition capacity with a very low clock frequency of few kilohertz and with a frame per 30 frames per second. In the same direction, in the LEHOE in 2018, actually, they proposed this. Intel basically released this non-commercial chip, basically that is called LEHOE, and it incorporates the self-learning capabilities based on novel neuron models. It is asynchronous and spike-based communication, basically. So this technology, this Intel's LEHOE chip is based on 40 nanometer technology process. And the model they use for the neuron is this LIF neuron, actually. If you see, this is the important aspect one can see. So this LIF neuron is basically the leaky, integrate and fire. This model is having a quite good resemblance with the biological or human neurons, actually. So therefore, this kind of arrangement or architectures offer a significant improvement in the power or computing efficiency, actually. And in this, they have used basically around 128 million synapses, 128,000 neurons, and they use this network on chip kind of routing protocols for performing these basic operations. In this direction, the latest one, just I think last week or just in 10 days, the Intel has also released this LEHOE 2 chip, actually. So this LEHOE 2 chip has been evaluated on wide range of applications. You can see from adaptive robot control arm to the visual tactile sensory perception, learning and recognizing new orders and gestures, fast database similarity research, and solving the hard optimization problems such as railway scheduling. And all these tasks this chip can do very efficiently and with a less than 1 watt power as compared to few kilowatt of power is used by standard CPU and GPU based solutions. So this is what the future computing looks basically to me, actually, and it is also the latest research development in the industry. And if we compare basically these two, LEHOE 1 and the LEHOE 2, then you can see there are total neuron cores, one's 128 and 128. The maximum neurons earlier in LEHOE 1 was 130K. It was basically 128K and 1 million now in the next one. Similarly, here the synapse was 128 million and now the number of synapses is 123. The maximum core processors per core was earlier was 3, now they have the 6 cores. So we can see that these neuromorphic computing is going to be the future of the computing to meet scenes, because lots of leading industries are working in this direction. And so the major challenge, if you see the designing of these chips, bringing new models, for these neurons, because traditionally that model that we use in artificial neural network or machine deep learning, that is the perceptron model actually. So realizing this perceptron model is difficult, specifically if you want to have better resemblance with the biological brain or biological neurons. And also nowadays we are using this spiking neural network rather than the traditional neural network. So these are the some of the work that I'm just going to show you that we have been doing basically. So we have developed some model for the leak integrate behavior in our lab basically. And this work is also got published in some good journals like IEEE Transactions. So this is a traditional CMOS transistors, if you see, with little variation in the traditional MOS transistors, where we have used basically the BiMOS transistor, bipolar impact ionization MOS transistor, and that by optimizing and by tweaking the sum of the parameters, these transistors exhibit a very good property like a biological neuron source actually. So some of the properties, let me just directly come to here actually to show you how this MOS model can be used. So this is what the silicon model that we developed, basically we optimize. And let's say, so this is what the post-silicon neuron, it can be used as a post-silicon neuron, and then there is a pre-silicon neuron actually. So if we connect these two neuron, pre-synaptic and post-silicon neuron, and perform some basic functionality, then it is having a good capability to recognize some small task basically. So for example, yeah, these are this is there some results if you see in terms of the spiking frequency. So this transistor is, or the proposed silicon neuron transistor is having a capability of ticking up to a few gigahertz. However, in the real world, we really don't need this much of spiking frequency. And these side you can see here how the spiking frequency keeps on increasing. If I just adjust the bias, which is also we can say we can analogous to the action potential in our human neurons or biological neurons. So this action potential can, if the voltage goes beyond certain voltage or resting potential, then a spike generates. That is called the action potential. So this device is successfully able to produce these kind of spikes because in the brain the information is processed in the form of spikes actually, or it is as per this knowledge available. So this is what the simple example we just showed you. We showed basically how we can use the same transistor to recognize let's say 4 different weather conditions. So if there are 4 different weather conditions, and if we train this neuron, actually biological or silicon neuron, for different conditions, then it is successfully able to recognize or separate these weather conditions actually. So with that, actually, I'm just closing because we are already at the end of this program. So without taking too much of time, I'm done actually. So thank you very much for giving this time. And if you have any queries, please feel free to ask.
Thank you, Dr. Singh, for very nice, nicely introducing the very important area of neuromorphic computing, and it's a very new area. And people from neuroscience and IT and electronics, and how they can collaborate jointly, and I mean, various devices can be possible with this. And of course, the variety of challenges you have shown that, just including that how you have moved from 180 nanometer technology node just in $1, and when you are to the 20 nanometer, and what challenges are arrived, and especially not in terms of only the cost, but the technical and other challenges are also arising, because as soon as you reach to 10 nanometer technology node, further miniaturization, either it is not possible, even if it is possible, it is very difficult to understand the process.
It's also very expensive actually.
Very expensive, and not only expensive, but the scientifically also is very difficult to understand what is going on around 10 nanometer. Right. So that is the limit of the physics in that sense, the quantum limit. So I'm sure this talk has been very, very interesting, and people must have got triggered in this particular area. And I can just ask 1 or 2 questions, if any, from the attendees to this very important area.
Yeah.
Yes, Subhash is having a question.
Yeah. Thank you for this nice presentation, Dr. Jawar Singh. Actually, I was curious to know about this spike model and perceptron model, because as far as silicon photonics, application of silicon photonics in neuromorphic design, they were advocating about the perceptron model of this silicon photonics, or neuromorphic, basically neuromorphic. So, but however, you are telling that we are adopting spike model for. So I'm a little bit in confusion. So can you tell pros and cons of spike model and perceptron? Over to you, sir.
Yeah. So perceptron model is very widely used by the software community, let me tell you. So realizing any kind of software algorithms they use and they develop this is perceptron model because that allow algorithms to incorporate quite easily. But if you want to implement it on hardware, then it is very expensive actually. So that's why the new type of models have came up. For example, this leaky integrate and fire model, which is having a very good resemblance with the biological brain also. So I'm basically comparing these two. So if I'm going to, let's say, implement this perceptron model in our at hardware level, then it is going to consume then we won't get the benefit of power that we used to get actually. And also it is going to take lots of silicon area and so on. So for software implementation, this perceptron model is perfectly fine, and even it is widely used. But if it comes to the hardware realization, then definitely we need to find out some alternative models. And there are plenty of other models, basically, like one of the popular model for which the even Nobel Prize was given, Hoskin-Huxley model, actually, if you remember, Hoskin-Huxley model of the neurons. And again, this Hoskin-Huxley model involves lots of complexity in terms of it is based on basically non-linear differential equations. So again, realizing that model in the hardware is a challenge.
Okay.
So lots of research is going on in developing a simplified.
Thank you so much. Yeah.
All right.
Yeah. Thank you, Dr. Singh. Any other question?
Great.
Yes, yeah. So let us thank all the speakers of this particular session and earlier session as well. So we just clap for everyone who has contributed and their talks. And now, without breaking for the next session, please allow me to start the next session just now. The panel discussion. And in the panel discussion, we have the speakers, we have the experts available here, and they have already joined. And so since morning, we are listening various talks, and people have talked about, started with the Dr. Mukesh Kumar's talk when he talked about the materials and device challenges, and what are the various opportunities, especially when you think of chip designing. And then he talked about, when people are interested in silicon, then people got interested in 3-5 compound semiconductors, and moving to the carbon electronics. So silicon electronics has moved to the carbon electronics, and the carbon electronics has its own challenges. So people have talked about many things, and especially when he talked about photonics, photonic materials and devices are having its own challenges. Followed by another talk, by Ms. Alka Jaiswal. She has nicely introduced a very important area. Those people who are new to this area, VLSI design, chip design, and all that, is nicely introduced the topic: chip design, fabrication, verification, testing, and Deep Sagal has very much more interested in talking about what SCL activities are there and how SCL can help the people from academia as well as the industry people. And and also, Dr. Trivedi, when he was talking about giving his lecture, he talked about the various challenges and opportunities in the electronic system design and manufacturing sector, and how one can think of going for Atmanirbhar Bharat. So, of course, the challenges, meeting out the challenges, and in the morning session also, I said that Government of India is pushing a lot to develop the electronic manufacturing hub in the various places in India, and it's a big challenge. So of course, the contribution from each and every corner is required, and we academicians as well as industry people and people from this scientific laboratories, we should come together and utilize the manpower, the skilled manpower we are producing in our institute, and achieve the target or the dream of Atmanirbhar Bharat through this. So, and of course, when the last talk was very, very interesting and very new area, it's neuromorphic computing, and which involves the people from even the social sciences as well. That neuroscience is very, very close to people from humanities, very, very important. And how this can be exploited in understanding the electronic designing electronic circuits is very, very important. And it has many challenges. So Dr. Jawar Singh has talked about those challenges. And the challenges, whenever there is a challenge, I always believe that there are opportunities. So opportunities for the people from academia, opportunities for the people from the industry, and of course people from the government who are sitting in the government as policy makers. So we all have to work together and fulfill the dream of Atmanirbhar Bharat. So with this, I would like to introduce the experts of this panel discussion. And Professor Manoj Singh Gaur, he was supposed to be here, but he's still busy in finance committee meeting. So he will not be attending this session. Mr. Rashmi Ranjan Mohapatra, I think he has joined. Welcome, Rashmi ji. He is co-founder and CEO at Exxon Technologies. So I welcome you, sir, for this session, and also accepting our invitation. Dr. Jawar is already there since morning, so I'm thankful to you, Jawar ji. Mr. Jatinder Singh is already here. Jatinder Singh is country head at IMEC. Hello, Jatinder ji. Nice meeting you, and thank you for accepting our invitation. He is at Belgium and Inter-University Microelectronics Center. He's from there, IMEC, and from there he's connected. So thank you so much for joining this panel discussion. And Dr. Vinay Singh is also there. I can see Dr. Vinay is there. Dr. Vinay is basically from management side, and he's more in technical management. So far we talked about the various technologies. We started with the material science. We talked about device technologies. When the technology is developed, and who is going to market it, and various challenges are the part of the management. So because some of the people, they have also talked about the incubation. People have talked about startups, those things. I think for that, the technology management people are very well required. So this is very, very important. Dr. Vinay is here. So thank you, Dr. Vinay, for accepting our invitation. Dr. Shashi Tantri, he is a professor at PS Institute, Bangalore. Dr. Shashi is there. Yeah, Shashi, we have been together in Japan. Shashi has done his PhD from Japan. And Shashi is also in this area. He has more than 17 years experience in industry, electronic industry, and then he moved to academia. So and one more person who is joining this particular panel discussion is Dr. Ramesh Vati. Ramesh is professor at SRM AP, Andhra Pradesh, and he has also contributed a lot on the electronic circuit designing and this area. So I have got a very good panel of the experts, and I'm sure that the topic we have taken into consideration in today's pre-conference, that is chip design, fabrication and testing. And that too, when we thought of as a part of the Madhya Pradesh government, as a part of the Indian government, that how we can inculcate this culture in Madhya Pradesh. And bringing in the morning, somebody was saying that "Aao Madhya Pradesh chale, wapas chale." So you cannot think of people bringing them back to their hometown or near to the hometown or near to their state until unless you are not going to provide the right platform to them. So, but in this digital time, I think there is no need to come back to your hometown. You can directly get connected through the virtual media, and like that you can be present in your hometown, and you can help your the local state government as well. And so with this, I would like to invite Jatinder ji, to start the session. And what is his vision about this chip designing, testing, fabrication challenges and opportunities, especially if you look at the Madhya Pradesh. Jatinder ji, please.
Thank you very much, Anurag. First of all, Anurag, I am joining from Bangalore, though I work for IMEC Belgium, but for last 2 years I am in Bangalore. So, uh, yes, so you see, as a IMEC, we work with more than 600 to 700 universities. So we know what kind of ecosystem is there worldwide, because we serve that kind of university, I will say, ecosystem. And I'm very glad that uh, under our Euro Practice program, we are serving almost all the IITs who are in the domain of chip design and chip activities. Uh, you know, uh, but I'm always very sad learning that, even though we are combinedly, India is much bigger than, combined Europe, but we have to depend upon a European program for getting our chips manufactured. Though I come from IMEC, but this is not. I'm not joining as IMEC here. I'm joining as Jitinder only here, and. What I feel is that probably we started little late the chip design activity in the academics. Okay, so my view is that, because when I look back, you will be surprised. The chip design activity in Belgium, which is probably the one of the most, that time it was the most insignificant country in Europe, 35 years back. Can you just believe that? Okay, and today what we see today what we see at IMEC, or today what we see, IMEC as a whole, is nothing but a combined effort of government, researchers, universities, collaborations. And today you see, after 35 years, they have become the technology leaders. My personal view is that in academics, we started very late with the semiconductors in general. We were teaching semiconductor physics. I in fact tried to do some kind of a study just to see, that when the semiconductor related courses were being, offered in India, we very well started with semiconductor physics, much, in the beginning. But in the chip design courses, more particularly, let me say, the VLSI design courses, the embedded courses came to the universities much later. I can only remember that maybe from last 5 to 6 years or 10 years, many colleges or top colleges started adapting it. I'm leaving the top 5, 6. Just top 5, 6. They are supplying the engineers only to US. Okay, those engineers are anyway not staying in India. So I see that. The why the in general the semiconductor could not flourish here, because the top 5, 6, 10 institutes which are offering these courses, those students, they were all going out working for the American companies. Nobody bothered to stay back. Then when this semiconductor teaching came into mainstream to other universities and colleges, by then it was already late. Okay, of course we have a very big design ecosystem here. We are very good designers, we are very creative people, but design as a service we are doing. Unfortunately, nobody took right step from the government or from the private industry in India to bring any attention towards assembly of the semiconductor, packaging of the semiconductor. There are only 2 fabs. By the way, I worked in Sitar for 20 years before joining IMEC, one of the previous fab in India. So this is what I feel, that maybe because we started late, we are behind. I think with this, I will stop and I will let other people to put their views. I am a very blunt person, so if anybody do not like my comments, please don't mind.
You rightly said, Jatinderji very rightly said, we started late, but no, whatever late is late. Now we have already started now thinking about it. The present government is pushing a lot to us, academia as well. And academia is very much interested to accelerate as early as possible in this area. And so may I request from academia side, Dr. Shashi, would you like to make comment on this? We started because you have been in industry 17 years and moved to the academia. So would you like to make comment on this?
Yeah, sure. Am I audible?
Yes.
Yeah. I think if I just look at the background, I think I started with electronic system design engineer and then moved on to VLSI design and then moved into different companies like product companies, service companies, and then finally now I'm in academics now. So here, because we here in PS University, we are very close to the VLSI hub of India. With your Intel being about 10 kilometers away, Texas Instrument being about 20 kilometers away from our system here. And plus all these companies also, when I was working as analog design head companies like Sanyo and Wipro, I had worked for these companies. So like Intel, Texas Instrument, and AMD and all. So overall, if I can just briefly touch upon this, the kind of work what these companies expect, say from the industries, like cater some small portion of their design flow, like verification or the analog layout kind of thing. So with that particular background or with that kind of jobs in the keeping that kind of jobs in mind, so many academic institutions who are in around say Bangalore have moved on to giving courses or giving teaching on the small portion of these kind of activities for VLSI design flow. In a way, okay, we are able to cater them to the requirement of that small job skills, whatever these companies require. But in if I look that into a one level up here, so nobody is kind of clearly know what exactly is whole of the design flow is about, whole of the fabrication is about. In a way, so that kind of expertise maybe in companies in around the hub like in Bangalore, may few know about it, but no one clearly knows exactly the complete design flow. And we in academics, we are just giving some job skills and giving them training on that. They get placed, okay, so our management is also happy that they are getting trained on, they are getting jobs and all. But overall, expertise at overall system level design is something very much lagging in academics, is what I can say. Yeah, this is what my overall.
Yeah, Shashi. Do you mean that, that, okay, let me just take the view of other experts as well, Rashmi, would you like to make comment on this? Because Jatinder has talked about that we started late, and Shashi is of the opinion that, there is a problem with the job and the people are not skilled enough, and there are very seldom, it means that, the academia and industry interaction is very poor. So maybe because of that, what we are teaching in the academia, it is not as per the expectation of the industry, and that's why I think there is some issue. So what is your comment on this?
Thank you, Anurag ji. Thank you, panelists and the participants. So I am actually the odd man out in VLSI industry. I started from software and moved back into the VLSI field. So I have been an entrepreneur for 15 years. And right now I run a company called A6N Technologies from Bhubaneswar. I'm talking to you guys from Bhubaneswar. So I came back in 2007 from US, and I was one of the co-founders of the first VLSI company in Odisha. So what, certain points I just jotted down listening to you guys are like, yes, we are late, but that's past, right? So, I mean, we can't do anything about it. So, and of course, we have to look at our, SWOT analysis, where is our strength and what should be our strategy in a global level. India is playing a global level game now with the leadership of our Prime Minister and, coming edge people in India understand that. So we do not have a product DNA. If we look at even software, we do not have the risk appetite or understanding. Traditionally, we have been traders from even in Odisha. I mean, we have a clan where they took these condiments and stuff to sell in Java, Sumatra, Thailand, and they took things from there and came back and sold in this shore of Bay of Bengal, and that is greatly celebrated here even today. So the DNA has been of trading, right? So that is where in the last 40-50 years I have felt that people from Japan, US, Europe have moved ahead because they took that risk. Now, still, the good thing to take away from that is in software and even in VLSI, we have been great in focusing on design, right? So we are a great design house. That is our strength. Even globally, a lot of software, chip design stuff are getting designed here in two ways. One in-house, the other, even it is getting designed in Europe and US. There are a lot of Indians who are doing that. The second thing is the ESDM manufacturing, is a chip fabrication as well as PCB fabrication for electronic products. That is already happening. You have presence of people like Flextronics, Dixon, Winstron. They are setting up large plants. Even people like Samsung, they are doing it here. However, chip fabrication is a huge capital investment game, and we are way behind, almost like 30 years in the learning curve if we compare ourselves to Taiwan or China, because most of the companies in the world went fabless depending on Taiwan and China. So apart from them, I guess Samsung and Intel are the only one who are still owning their own fabs. And they realized that, everybody realized that lacuna or shortcoming during COVID, because if you want to get the dependency out, you are not ready. So I guess that is something the government and the industry who have deep pockets should work strategically in parallel, and we have to burn the rope from both ends. One, since we are strong in design, we should stay strong there, do a lot of design activities, product oriented, and for even most bleeding edge, cutting edge customers in this world, keep doing that, and in parallel work on the fab manufacturing also. We'll never get there overnight, but someday we got to break the transition from 10%, 30% down 15 years, we'll be somewhere. Now, there is no awareness in the academia. If you ask the students, most of the people who like us, like they want a job, right? So they do not have the choice. In some companies coming from campus, even if it's a ETC or electrical engineer, they will choose that. They will go to Infosys or TCS, whatever they lay their hands on. So we have to create awareness at much younger level, even before 10th or something, so that they can choose things. That is not there, is what we have observed. And also we need to market it to the people of the place, like this is for Madhya Pradesh. So, no Japanese guy is going to come and build things in Madhya Pradesh. It has to be people of Madhya Pradesh, right? So I built this company. This is my second startup, by the way. The first one went through acquisitions, and we brought in two North American companies to Bhubaneswar. They didn't have Indian footprint. So we have to create such positive examples, because of which the others start believing in themselves. And I know it's a hard thing I'm saying, but I can't see any other way how we can mobilize these things. And once we create these positive examples, more and more people always like their place. People who have grown up in Indore, they will definitely have the affection, the attachment to this place. But they are looking for career opportunities. They don't believe it can happen there. So that's a perception change people need to do. And obviously some guy from Thailand is not going to do that there. So I am doing it in Bhubaneswar just because I am born here. It's like when we used to play cricket in schools, there are two teams, like team A, team B. So if I'm in team A, I'll play for team A. There is no other consideration. Similarly, for Indore and Madhya Pradesh, it has to be some kind of marketing and awareness we have to build in both ways. And regarding industry academia collaboration, I see it happening. Though the thinking is different, but I see that academia is interested to work with industry, and industry is interested to work with academia. And our company is actually working with 3 universities, IIT Kanpur, IIT Indore, and we are talking to IIT Roorkee right now for combined execution of projects. I think it will get better with time once we start understanding each other. Thank you.
Yeah, that's very nicely, as the entrepreneurs, perspective is very, very important. Your views are very important. And very rightly said that a SWOT analysis is very, very important, need to be done at our own level. And what you said, very true, that awareness should be started at early stage of learning. Maybe at the stage of schooling, because Jatinder is also of the opinion, and you also of the opinion, that we are 30-35 years, lagging in, reaching to the people who are doing in the Taiwan and other places. And and another issue that what Shashi has raised is also very, very important, that academia and industry interaction is very, very poor. But why this interaction is very poor? So in that case, what you said rightly, Rashmi, that positive examples we need to set from the academia side, and then we can think of that industry will come to you. And not only that, industry will come to the people who have gone from your own place, and they move to other places because of the much better facilities outside, and of course the better jobs. So they will get attached, and they will get attached back. They will come back, and they will start participating in building your state. So yeah, this is very true. Now I think should I invite Ramesh? Ramesh already is in SRM Andhra Pradesh, and he's in academia. So let's see what is his view, Ramesh ji.
Thank you, Professor Anurag. Am I audible?
Yeah, you are audible. Yeah.
Good evening to all the panelists and the participants. Yes, I do agree with the observations of the Dr. Jatinder and Dr. Ranjan. So what we need to see is that there is a big gap between academia and industry for multiple reasons. So usually industries in India, we can observe that they are participating at the later stage. Mostly, usually they come to take the final fruit of for the placement. So if we can have a better mechanism to involve them right from the curriculum and some kind of training, some kind of courses, like we can develop such that some of the courses are being taught jointly by the industry and people and the faculty members. I think the students will have better opportunities to have the work on some cutting real-time projects, and better learning will happen. And I think that will may possibly minimize the gap between the academia and industry, and maybe both the communities can gain in the long run. And so I feel this is my observation. So another thing, I think I'm very happy Madhya Pradesh government is making these efforts to increase awareness among the researchers and trying further. So one thing I think possible thing can be looked at is like pulling all the resources of the national resources available in the country, not only from the government. What are the different researchers are working in different domains? What are the expertise available? So the continuous awareness and training sessions can be arranged for the students and the engineers, the researchers working in the domain. That will make prepare the better future. At least whatever the late we are there in the back, but if we want to build it, there has to be continuous these learning sessions and activities have to be done in a more continuous manner, not just once in like some. So these things can be done. I think we'll be able to meet some of these fill the gap, and I think we'll be moving in the right direction. And similarly, we need to increase, like a lot of people are not aware of several design contests or e-fabless opportunities available. So we need to increase that awareness among the faculty members, researchers, students. So I think some of these things will prepare us better for the right direction, I feel. So thank you. That's what my observations.
Yeah, thank you, Ramesh. You are also of the same opinion that the awareness is very well required at the early stages, and we should not wait for the later stages. And that's why I think we are far behind Taiwan and other places. May I request Jawarji? I mean, you also have a lot of experience working in different institutions. You have seen variety of students in different places. And the ecosystem what you have seen in Madhya Pradesh, and now you are taking in Bihar, and I know you have also been to UK. So can you make a comparative analysis how you feel about this, and that how the Madhya Pradesh people should move ahead, move forward, in this case of achieving the goals of bringing the people back and starting, somehow motivating the young entrepreneurs basically to start their ventures in this particular area, and how government can do something for them, because until unless the government is not having the right policies, it's very difficult to motivate the young bloods to come to this area.
All right. So thank you, Anuragji. So I'm really clueless on this website. I have read many articles recently. Also, the government is planning, or government is working to get something from Taiwan, or in the past also we have seen, right? But I'm more towards this fabless or towards this design part rather than fab. And recently we have seen many good opportunities and many good new policies by the government of India, specifically we talk about the startups. So if we develop our system or our culture for this fabless startups as a design hub, semiconductor, this chip design systems, or there's a design hub, I think we already are there in that business. But if we can further expedite this in the future, technology, like I mentioned, in the neuromorphic is going to be a new area where lots of people are working to replace the GPU and CPU because they have a very low energy footprints. So new kind of chip design aspect, or also as that Madam told in the day, that the design time already, we also know the design time or design cycle is quite longer specifically. So if we can use this AI for shortening or designing the chip, something like this. Actually, I'm really don't have too much about this actually. So I would like to close with this.
Thank you, Jawarji. I think now we have the person from Dr. Vinay is there. Dr. Vinay, can you just unmute yourself, Dr. Vinay? Vinay, please unmute yourself. Unmute yourself.
Am I audible, sir?
Yes, you are audible now. You are from technology management, and a lot of things needed at the side of the management. Starting from the organizing the program for making the people aware about the technology challenges, opportunities, because the job satisfaction is very, very important. But before that, they should get placed properly. So until unless they are not having enough food in their stomach, how they can contribute. So that is very, very important. And you have also been associated with the startup and incubation activities of IIITM with me. So I'm sure you can make a comment on this, what the panel experts have said, especially when thinking about the supporting the people who are interested in coming to the startup India program. Yeah.
So based on the discussion held from different panel experts, one thing I from Mr. Rasmiji, and who is focusing on the poor connect between industry and academics, number one, and one input from Mr. Ramesh, that is awareness among the stakeholders who are the right people to be involved for the technology design, technology development, and the person who are exploiting this technology for the customer purpose. So I would like to mention few understanding based on the specific need of the technology, that is chip design, fabrication, and testing facility. So I understand based on my past experience, interaction with industry of such domain, and having different understanding from different cases, there is need of mechanizing the process of this designing, fabrication, and testing by arranging two basic phenomena of technology development, that is exploration of the technology and exploitation of technology, where exploration of technology will take care of experimentation and development. Normally, just to handle such thing, probably due to the being a cost-intensive technology, these arrangements can be distributed among different R&D setups, including industry R&D wing, academia, who are deeply involved in this chip designing and chip manufacturing philosophy, and the second part, who is basically taking care of the development of these experimentation that would be facilitated by different R&D units, that is hardcore industry, who are willing to come over here in Madhya Pradesh, so that there is specified technology can be commercialized within the India and outside of India. So this development part is probably, there is based on my understanding, there is lack of such professionals, or there is again communication gap, or some policy gap, or some strategical gap existing between academicians, government, and these industries, or these industry fellows who are doing very well in abroad, but and having their footfall in India itself. Especially I'm talking about the Madhya Pradesh, right? So once the government will ensure them to come up over here through policy, to provide by providing different subsidies, by providing different supports, by providing lands, by providing skilled manpower, so that at least industry feel confident to put their foot over here, and again immediately where to commercialize this technology for the purpose. Probably India is big customer oriented economy. So being customer centric economy, probably this opportunity was exploited by China, Taiwan, and other Southeast Asian countries. So probably this is right time. Oh, no doubt, Professor Jatinder is mentioned very clearly that we are late, but no doubt for this particular time, thanks to COVID, that given multiple opportunity to learn to us. So in this time, due to the economic condition of China, where there is crisis of energy, there is crisis of basically natural resources, at least India can win this opportunity by putting their foot in such particular domain as early as possible. In that situation, we have very clearly exploitation opportunity, we have very clear developmental opportunity, and we have stakeholders who are willing to develop. We have experimentation set up by having different academic and R&D institution over here. So only synergizing is a right strategy where intervention of government is very necessary. Considering this initiative of this basically MPVS kind of fest would definitely facilitate to fulfill this particular objective in this particular direction. So initially, I think it's opening remark from my side, sir, and probably the discussion must be open from your side.
Okay, thank you, Dr. Vinay. And now I think people have talked about many things, and you added to this that exploitation and exploration of technology is very, very important. And you have observed that there is a strategic gap whether you talk about the policy makers or you talk about the people from academia, and even I will include the industry as well, because the initiative should come from their side as well. I know, because we Indians normally work in force. So whenever there is a force, we perform much better. You have seen that our team, Indian team, also perform much better when they are under pressure. So they have to achieve a very high target. Anyway, so now the discussion is open now. I think Shashi would like to make comment on this, or for further how to proceed further, because ultimately the idea is basically Viksit Pradesh and Atmanirbhar Desh, right? How to achieve this? Having these contents in mind, we know there are many ifs and buts, right? But what we can propose to the government of Madhya Pradesh as a panelist, and because I'm just noting down your views, and I'll submit this report to the organizers who are the main organizers, and they will pass on to the policy makers of Madhya Pradesh. And yeah, Shashi, would you like to make comment on this further?
Yeah, I think right now the scenario, if I look at global semiconductor scenario, so right now designs are getting carried out in US and verification is happening in India, and fabs are happening in China or Taiwan. So that scenario has to be changed, where the other two parts of the activities here has to be focused more with more and more design it's getting done in India, and more fabs facility with a low cost, where academicians or students can avail those facilities for fab has to be initiated more with definitely support of Madhya Pradesh government or government of India. Yeah. Over to you. Yeah.
I think, Mr. Ramesh, I think based on this Siddhar's input, I think you must be having certain comment and an addendum to this venture.
Sorry, sir, exactly. I missed that point. I was thinking slightly different. I was also thinking the leading institutions in that state, there is an IIT or IIIT or NIT. I feel they also have a better, I think, more role to play in training the younger researchers. I'm feeling like so. If they take a more lead and contribute, I think the gap and they can prepare better for the aspirations of the state. I can feel. That's what I'm feeling.
Rasmiji, based on these inputs, what kind of arrangement can be facilitated through state government, at least to attract the industry in Madhya Pradesh, especially in this particular domain? What is your take?
So basically, industry focuses on business. So there are two kind of activities which will accelerate the industry setting up in Madhya Pradesh. Are inviting them. Second is forming a collaborative team which will know what an industry is trying to do next. For example, if Cisco is thinking of a next center in India apart from Bangalore, it can be in Indore, but then you have to know that Cisco management is thinking that. So to be able to do that, there has to be a team which interacts with the industry, senior leadership of the industry. So that is one way you preempt their thought and provide things like land and subsidies in electricity, taxes for initial 4 or 5 years. So I will just give one example. When we got acquired by Semtech Corporation in US, so obviously these days there is no global company in US, Europe where there are no, you will find Indians in leadership role. So you're talking to a BP, most likely that's an Indian or maybe Chinese. So so they have their roots in India. So they can go to Bangalore, Hyderabad. Many discussions actually start. So the way that can work is they also compare other cities globally, places like Shenzhen, Ho Chi Minh in Vietnam, and stuff like that, to have a center. So how it will work is that if there is a collaborative team which knows this, then you can provide tax benefits, facilities, completely ready to move in kind of facilities. Because in our case, what happened was they compared us these facilities what we wanted to provide in Bhubaneswar. They compared it to Shenzhen, Mexico City, where Shenzhen was providing 20% of the staff that are being hired locally. They were giving a 5-year no rent facility, completely globally furnished and ready to move in. Those kind of facilities business wants to set it up. And once they set up there and operate for 5 years, it's not easy for them to move out, right? And the collaterals that get generated from that is that local people working there develop skills. So I did not become an entrepreneur on one day. It took stages of mental conditioning and being able to dare to do that. So how that happens is first you get exposed, then you generate skills, then you understand the business, then you say, okay, I can do it. So that transition also will happen in a lot of youngsters in Indore. So after 5-7 years, many more people will start their own companies. So keeping in view, there has to be an agreement between government, local industries, and academia to attempt this kind of a thing, so that you attract external bigger companies and encourage people to take more entrepreneurial role around that ecosystem.
Jatinder ji, if you look at these philosophy, which is still in theory, especially in this particular context. So, based on your experience, what kind of risk you are perceiving in Madhya Pradesh, based on that, industries of particular domain cannot be attracted over here? Or what kind of pitfalls that need to be encountered before inviting such professionals in Madhya Pradesh?
Okay, so I have a slightly strange view here. There are two things, when you want to attract people to come and work for some companies in some location. Okay, now the benefit of working for people, let us say in the metros in Bangalore, Hyderabad, or Pune, is that they get an ecosystem where they know that if I have to kind of jump to another place, I have it around where I am now working. Okay, so that is where our especially for we all come from middle class families, most of us. Okay, and their first job, even though in the university they may have 1 or 2 or 3 choices, assuming that a student gets placed in Bangalore and at the same time get placed in Madhya Pradesh, let us say with a company in Madhya Pradesh, even giving them a little higher money, still that guy would like to come to Bangalore, because he knows that if he goes there, he will have more opportunities. But that, nevertheless, that should not get we should not get discouraged by that. What Rashmi said, I totally agree with him, is that you have to uh, bring people, large companies first. I have already seen some companies moving to Madhya Pradesh. Some big companies, they have their big campuses set up. Same way, I'm from Punjab. I have seen how in Mohali, big companies, they have some large centers. And believe me, after 5 years, it is difficult for them to move back. Okay, same thing happened in Kerala. For example, we had a opinion that because there is a certain kind of government there, it is very difficult. But today you see some of the large tech companies, they have huge campuses in there, and now they are all good revenue generation centers. So I think the first step is to bring some big people to your city or to your state, give them some incentives for at least 5 years. Other people will automatically start coming and start using that, those facilities, or they will start coming to those places, because now they know that a lot of manpower is there. Then eventually people who wants to remain in Indore or remain in Bhopal, they would also see that, look यार अभी एक company है, इसमें जाऊंगा तो एक और है, एक और है, एक और है. So that's how it goes. Okay. The second thing, which I will say that, what IMEC follows or have been following for last 35 years is collaboration, collaboration, collaboration. We cannot survive without collaboration. We always tell whenever, even our corporate events, that that should be the DNA of every employee in IMEC. Okay. And we have mandatory 56 hours of training. Now, if you have to say 56 hours of training, that means your 7 working days, you have to have a training, and that is in the KPI, the key performance indicators, which is very much counted in your yearly appraisals. So I have seen that this kind of performance indicators is missing in many companies. Okay, when especially the startups, if they have this kind of a performance indicators, and when an engineer joins them, they feel that oh, this company is giving them opportunity to learn. They are paying for some additional courses. These are not big time money we have to spend. This is only the mindset that as a promoter of the company, they should at least give, let us say, 5 days freedom to their employees, that look, man, go and choose any course. Let us say I'm paying 50,000 rupees. Go for 5 days, do that course and come back. And I will say, I can assure you that that person will come so happy back. Probably he's not going to leave for another 1 year thinking that another 50,000 is on the table for him to learn something new. So this is something which I have seen even in the large corporate in Bangalore. It is missing. People are conducting the corporate trainings only for the namesake. They are also inviting academia. Again, I'm sorry to say, only for the namesake. They will write in their books that the training has happened for the complete day, whereas the professor is there only for 1 hour, which is actually very, very unfair. So we should create this kind of these benefits we should give to our employees. Okay, or we should tell the companies, let us say in Madhya Pradesh, that why don't you promote this? Okay, as academicians, you invite them that, look, we also have some summer holidays, we can come over to your place and conduct. You send your people to IIT. I am sure that in IMEC we take hundreds of interns during summer. And why they come to us? Because they get a good experience. Even for 7 day, 8 day, 10 day, they come and go back. And believe me, those students, they learn a lot. Same way, teachers, they are allowed to go to the universities to teachers are there allowed to go to the companies and collaborate with them. So I think that collaboration is missing. We are having many schemes to collaborate, but eventually we do not define the outcome of that collaboration, unfortunately. I think that's all I want to say here, because this is what I have seen, that bringing some success somewhere. I think the same model can be repeated here.
Yeah, I think very rightly said, Jatendra ji. You have pinpointed the nerves of the industry, academia, as well as the government, and this is very, very important. Sometimes these kind of comments very well required, and they should be taken in very positive spirit. That what is actually needed, what is our role. I think the Rashmi will agree with this, that when he talked about SWOT analysis, you really did the SWOT analysis now. that whatever our weakness, I mean, people know about their strength, that is true, but accepting their weakness is very, very difficult, very challenging. And it's very important that we should accept what is the weakness of industry, what is the weakness of academia, and the complete ecosystem, how it is getting affected because of that, the attitude. So that attitude needs to be changed, and then only we can think of having what you rightly said, Jatendra ji, that we normally talk about collaboration, but do we really know what is collaboration? Are we doing collaboration? So we are just, on paper, we are writing, we are collaborating with some X or Y, Z from industry or from academia. But what actually means the collaboration? The collective effort what we are doing, whether we are really contributing the community to the society, and it is going to get benefit to the government or to the country, that need to be realized in the beginning itself before actually making plan for collaboration. So that is very well required. And what you said rightly, the performance, how to improvise the performance of the employees, basically, that is very well required. That the examples you have rightly said, it is not only in industry, but in academia also. We have seen the in institutions, government organizes various orientation programs, right? But how many people are really attending those orientation programs? They are bringing back, they are attending, they are enjoying their life, right, on the money of the government or the institution, and they are coming back with a certificate. That's all. But do you think that really they have learned something, and they are going, when they are coming back, they are going to contribute? So there is, there should be proper policy for that. It is not only for the industry, but academia people should also think about this. And I'm sure, if we'll keep these things in mind, system can be think of having a very good ecosystem, whatever the field we like. Of course, there are challenges with the electronic industry, lot of challenges. And if you look at the IT industry, they have excelled a lot, and they have followed very good practices. Like for example, you have said that you are allowing the number of interns. Like, and in computer science, yes, IT field, there are a lot many industries. They are attracting the young brains. They are attracting the even faculties. They are allowing the faculty to become mentors and they are also paying them. So that is very good practice. But in electronic industry, its condition is not very good. But I'm sure that with these deliberations and we will come to a conclusion that government will also get pushed and will also get triggered. And I think Santosh is here. Dr. Santosh, I'm seeing you are here. Dr. Santosh?
Yes, Anuragji, I'm here. I'm driving, but yeah, I'm listening all of you. Yes, thank you.
So no, because you are here, you are backbone of this complete program. So we would like to hear you as well, because you must have heard us what we are interacting for the last 1 hour almost.
Yes. So yeah, I'm just noting down a couple of things with my colleagues. I'm driving. Okay. So
okay, you are driving. Okay.
I'm driving.
I'll not disturb you. You reach to proper place first. Okay.
Yes.
And, yeah.
I thought at least I should listen all of the conversation, and we can submit the recommendation to the ministry.
Yes. Okay. Of course. Jawarji. Please continue. Jawarji, Dr. Jawar.
Yes. I'm here.
Can we make a concluding remark from each one of you, maybe 2 minutes or 3 minutes remarks, because we are about to close this session in just 10 minutes or so, 10 to 12 minutes.
Yeah.
Remarks from start from your side, Jawarji.
All right. So I would suggest, let's say, propose to have some kind of design hub actually, and set up a kind of programs where these design activities, chip design activities, can be given priorities or given some incentives. This is what I believe. I think.
Okay, so can we, Jawarji, can you just club what somebody has said that can we think of starting in early stages, like I think Rashmi was telling about this. Can we think of about the people, making people aware at the early stage? And what you're saying that proposing designing hub, can we involve the school students in that?
School students may not be good, but the students
I'm just thinking about this, because if you are trying to develop a complete ecosystem, so why not to at the school level? Because these days, students at the level of the 11th and 12th, they are smart enough. They are developing very good, smart kids. They are developing, nice apps. So because these days it is not only the electronics which need to be understand, the IT is very equally, very well integrated in that. So can we think of? I mean, I'm just having
I little disagree with this actually, because this is not that just developing a app for which already plenty of very drag and drag kind of.
My idea was simply making them aware the area, the field, because when they are moving to join some engineering institutes, they should have something in their mind, not only just for sake of joining a course, rather than they should have complete plan of action in 11th and 12th itself.
So some kind of a 1 week interaction or these kind of things may be okay, very short interaction or kind of exposure or exhibition things may be okay. But I think if you want to have a good interaction or more manpower in this domain, actually, then the undergraduate, final year of undergraduate or postgraduate should be given the priority actually.
No, that is true. That is true. Yeah. Yeah. Jatinder ji, would you like to make your remarks?
Yeah, I think I missed answering your previous question. I remember that what Madhya Pradesh should be doing to enhance this ecosystem in the state. I will say that again, because you have 3 to 4 very good institutes right now also who are the part of this program. Okay, I believe that this kind of let us say semiconductor related stuff is very expensive. Okay, so if you are spending money, please spend in a one centralized place and become you all universities together, you collaborate and try to do some interdisciplinary course so that everybody can go and use that. And once you spend the money in one place, obviously I will request maybe I will suggest you to spend that money wisely so that at least you have some lab facilities, design facilities, everything in a single place, and let people from all other collaborative university use it. Now this will help you in twofold. Number one is you will have your increased interaction among yourself, so you will get to learn from each other much more than what probably you would be doing alone in your own institute. That is number one. Number two, because now it is not only one oscilloscope lying in your place and another oscilloscope lying in another place. Okay, now it is a complete facility which is lying together and where you can do multiple things. Now this will also attract let us say entrepreneurs like Rashmi, who probably sees that, look, if I have to do a chip, at least I can test it in let us say IIT Indore because there is a centralized facility available. And then they can start thinking of looking at the things that, look, these resources are available and they are all centrally located in one particular place. So this will help you actually in two folds. One, to create a facility which is complete, because I'm seeing the comments in the chat about this INUP programs, and I am very much aware of that. Now, unfortunately, what had happened during that time, that as our MITI, or that time it was DITI, or DST, it must be one of this program. They throw the money everywhere. Some 50 paisa here and 1 rupee somewhere there and 2 rupees somewhere else. That money is sufficient to run this kind of a facilities maybe for 1 year, 2 years, 3 years, 4 years. But what happens after that? Now most of these INUP facilities are facing problem. They are not getting funds to continue to upgrade, number one, those facilities, not even having sufficient fund to maintain what is there already available in those facilities. So therefore, my concluding remark to you will be that ask some government support. Whatever government is ready to give you, please spend in one centralized place. Spend it wisely, make it complete, so that you have, at least you can do one part of a chip in that. Of course you cannot put a fab, but at least can you do a test of the entire chip? Can you do the characterization of the chip after it comes back? Or then again, can you have some small packaging machine available, something like that? Can you have a probe station available in your centralized facilities? Please do like that. I think that would be my concluding remark. Thank you.
Yeah, thank you, Jatinderji. Yeah, I mean, you nicely concluded that what actually needed I mean, at the side of the government, and we can also think of making this design this place of one centralized facility by taking the support from the similar interest organizations. They can develop one center. I mean, instead of taking money from the government, they can start their own center. They can make a collaboration, and yeah, that is very important. Rameshji, yeah, do
Yes,
you
sir.
like to make?
My concluding remarks is that as we are, the government of Madhya Pradesh is making right efforts in the right direction. So it needs to continue this educational opportunities for the in a continuous manner, not just once or twice like this. And also the facilities, like I feel like this kind of program is considered to be success when, like, let us say there is a facility in IIT or some premier institute, and there is a collaboration as you're talking. There is a chip comes out, let us say, maybe may not be within a 1 year, maybe 2 years or later. Faculty from IIT and faculty from a nearby colleges, engineering colleges, and the students involved, both of them come together. I think this kind of program can be considered to be like successful in the long run. That's so. This training has to happen in a continuous manner. So the facilities have to be open for all the people of the interested people in that region. Then it will continue and sustain in the long run. So thank you with that.
Santoshji, are you making some comment?
Hello, Anuragji, can I say something?
Yes. Yeah, please. Why not? Yeah.
Yeah, so thank you so much, all the panelists. And yesterday only there was a meeting to establish the student chapter of VLSI Society of India. And in Central India, the responsibility is given to us. So very soon we'll establish the next 1 month or so for VLSI Society of India student chapters. I believe that we will have several such activities where VLSI Society of India will fund so many things. So I believe that in the coming months, we will have the right steps for the growth of Madhya Pradesh in semiconductor. That was the one quick kind of initiative which I feel that we are going to start soon in collaboration with VLSI Society of India.
Very good. Yeah, good. Yes, Shashi, your comments, and yeah, quick comment. You please unmute yourself. Please unmute yourself.
I have 2 quick comments to make here.
Yeah.
One is the training of the VLSI design flow can be given to students at very early level, like diploma students or even 10th and 12th grade. We had done that previously in one of the company called Sankal, which worked well, and we could able to attract many young talents there. So that is something which with government initiative, if that can be accommodated by giving these trainings for smaller part of the flow, that is something which I can recommend here. The second part is I give you example of Toyota here. So Toyota initially came to Bangalore with a small setup here, and then they grow and they attracted many other ancillaries of the Toyota. So Toyota being the center point, and then many other companies came in there with the support of Toyota. So in that way, if government can attract one key company there, and that would make the system to grow in that environment. So that is the second kind of suggestion what I can mention here.
Yeah, thank you, Shashi. Rashmi, your remarks.
I mean,
sir.
Yeah, somebody saying something. Any questions?
Let me see. He want, huh? Huh? Yes, Gaurav, would you like to make any comment?
Sir, just I want to say something regarding this. Say, sir, the SMDP was the program which was started by the government, and I suppose the first phase was that first they were providing the license for the tools, and in the second phase they started to initialize the fabrication, means chip tape out. They have collaborated with the SCL, and I realized that in the second phase of the SMDP, this is the government program, many institutes were submitting the chip tape out. So they get the idea. So if we are talking about the fabrication, then this type of program can help, because at the initial level, say suppose it is government issued, sometimes we may get the software, but for other institute, and also it will be very good if we get the license of the software, so that it will encourage the students in the VLSI stream. Okay, they can learn a lot, and because this was the first step, they in the second phase of the SMDP, they learn to fabricate, means they are going up to chip tape out. So it was the initialized phase, but now I suppose if it will be continue by the central or in this state level way, so it will get the one momentum, and from that momentum student get the idea in futures, or the MTech student, whatever they are coming, they will see that how can we reach up to chip tape out. And also we can also show the some, because say if I say about the IIT Jodhpur, or basically I personally discuss with some IIT Jodhpur faculty and some research scholars who are using the very for testing of the chips, they are using the very small setup, but they are able to test it. And so that's why we can collaborate with the IITs, and they make some arrangement for testing also. Means if they give the idea for testing, as we got the idea about fabrication, then definitely in the coming days we may get the idea that how can I start, how can we fabricate the chip, how can we test it, because fabrication and testing both are important. So if we follow some guidelines, say as SMDP, we can start from a state program, we can provide the software, and then we can keep some target that each institute should submit the chip, each institute should submit something. So from initial, step by step, we can reach something. We can reach into some remarkable position if we talk about state level position. So at that time the industry may come and they will see that each institute is making the chip, and so in this way I suppose it may help, sir, for MP government. Yes, sir.
Thank you, Gaurav. Now you rightly said that SMDP program is very good program, but the output, and we have to measure the output. What is the output coming out of this project? And government has invested a lot in SMDP program. A lot of money has been invested, but how many people are aware? There is a question mark. There is a debate going on.
Sir, in my panel, only one student submit the chip, and every institute has submitted the chip. There were the 6 institute. So, sir, I agree with there was a lot of money.
I'm just making comment that what government is thinking about this project, because you are saying that it
is okay, but the thing is, what is the output? So I can just say that the faculty are getting the idea to.
Output is a bigger umbrella. Output is a bigger umbrella. Output is a bigger umbrella.
No, sir. Many students get the idea for chip tape out. We have sent the chip for chip tape out.
Let us we have to close the discussion and all this, because other speakers need to.
Yes, sir.
Okay. Yes, Rashmi. Yeah, we would like to hear you on this.
So baby steps are required. We are already working as a company in collaborative products with IIT Indore anyway. So we can extend that to chip design projects which are not like on hot deadline roadmap. Then it will cultivate a culture of people, engineering students getting aware of this. MTech students, BTech students, and PhD students. Some small projects can be executed. That will be a start. And of course, at the other end, at bigger level, as everybody in the panel understands that bigger companies need to be attracted. So there has to be a strategy. So I think that's my submission. It has already started. That's a positive thing. So.
Yeah. So I think Vinay, would you like to make a final comment from your side? Because I think.
Please, sir, whatever we discussed about this collaboration part, that is really very fruitful way to bring out the overall productivity of whole setup. But another associated risk is protection of this intellectual property in collaborative mode. That is probably a kind of risk that usually industries fear to put their step in the collaboration form, which should be very much clearly explored from various means and modes. Number one. Number two, if government can facilitate a central manufacturing facility, then again, who is going to get production from there? What kind of design should be placed in that particular manufacturing setup for the customization purpose? Now, how to protect intellectual property over there at manufacturer's level is again a collaborative step with clear-cut policy. I think this portion should also be well taken care in the whole process.
Okay, thank you, Vinay. There is one very active member, among the attendees, Subhashji. So I'm just seeing chat box. He's making comment on.
I think
one of you.
comment is very important, sir.
Subhashji, can you just switch on your video, please, Subhashji? Yes.
Yes, sir.
Yes,
Yes, sir. Yes,
so thank you
Professor
very
Anurag,
much
sir.
for making this session more alive from attendees side. And I would like to hear you as well. What is your comment on this?
Thank you, Anurag, sir. Most of the things I have already written in
Yeah, I have seen in the chat box.
so
That's
that
why
it looks like a participatory event. Yeah. Thank you. Yeah, as Jatinder Singh sir told that we are very much lacking in field of chip designing, and in fact myself also came very late about this entire design cycle. That too through edX course run by Professor Lucas, and through his course, and our chip used to design at University of British Columbia, Nano Tools, and then there was another great endeavor by USA under AIM Photonics. So they also have run this course, PIC, Photonic Integrated Circuit. So as a learner like me, there may be more. We are getting this kind of information from the foreign countries through their outreach program. However, these things are missing in India, whosoever are like leaders in IITs, NITs, and central universities. So this kind of outreach program should be there so that people should know the facilities available within India. Like today, semiconductor electronics facility they have, but their multi-project wafer facilities are not accessible as such to people. In fact, invitation should be there and proper advertisement should be there so that first generation learners, second generation, means I mean to say students, say PhD scholar, there is a young researcher, then in fact experienced researcher can take part in that activity, and this prototyping should of course reach to industry standard so that scalable product can come into market. So however, some of the chip fabrication facility may be there, but it is only for strategic purpose where defense related activities are going on, and those cannot be open for everyone in India, so far I know. So that is why there is a priority should be given from the government side. Now I was keep telling here INP, both places were started with great what is called this money involvement is there, but now it is not functional. So this is again a wastage of government money. It should be revived somewhere. It should not be stand still because of the large number of researchers were getting benefit out of it, particularly colleges and universities. So far I know. Yes, with this I would not take much time. Thank you so much, Anurag sir, and taking this great initiative. Although here participants are less, in fact, I also invited my scholars, students also to take part into this activity, but I did not know why they are so passive. A lot of hard work we are doing here to advertise, but even after our advertisement, people are not taking
I think that's why most of the speakers are of this view that awareness is very, very important, and at the early stages of learning, and then only they will realize the importance of this when they will come to this particular stage. Because I have seen that most of the students, the attendees, they are either from MTech or they are scholars. So how many of them they are interested in this domain is very, very important. And making them alive to this particular ecosystem, it is our responsibility. Yeah. So as well as academician as well as industry people, this is very, very important. And so we reach to this final moment of this particular today's pre-conference, and we have seen a lot of very good deliberations, interactions, and thought processing on how to bring the people back to the mainstream, and the people reconnecting them to their own alma mater or their own state, and helping the government basically in devising the right policy. That is very, very important. So policy not only in terms of providing the funding to the entrepreneurs, funding to the startups, funding to the academia or faculty members for doing the research, but a collaborative effort is needed. That is very, very important. So in today's program, I think we have heard one keynote talk in the morning, and 4 very interesting talks, invited talks by different experts, starting with the very introductory and very important introduction is very, very important, the chip design concept by Alka from Intel, and then followed by other 2 talks, 3 talks. One is by industry person from Deep Sahgal. SCL is contributing a lot to this particular area, we know very well. So he also talked about collaborative effort, and he has shown that how the people from different academia, they are developing the chips blueprint, and it is going to the SCL for verification and testing and all that. And then 2 other important talks by Dr. Gaurav Trivedi from IT Guwahati, and one talk by Dr. Jawar Singh from IT Patna. So I'm sure, and besides this, this particular discussion or interaction, rather I should say that the think tanks of different fields, especially they come to this particular platform, and I'm sure because I have noted down the various points, and I'm also ready that if you have any plan of action you want to suggest, you please just send me through email. I'll compile all these things together and send it to all of you, as well as to the main organizers of this conference, Dr. Santosh and his team, and because they can directly get connected to the government of Madhya Pradesh, and your people's advice, your advice will be taken care of very well by the government of Madhya Pradesh. Because I could see some students are here. One attendee from the student side, I can take one if anybody is interested to ask any question, because it's a galaxy of an expert sitting over here from different domains, and any student who is interested to ask any question, because this is what discussion we are making, it is for you people. And Subhash ji rightly said why people are leaving the session now, because the patience is very important actually, and so that is missing anyway. So I think overall session was very good. I feel personally I enjoyed a lot, and let us thank all the speakers and all the experts who have been involved since morning, and they have been with us, and they kept waiting for their turn, and not only that, they kept listening us, they kept messaging us, And finally, when you reach to this panel discussion part, and we reach to this one final remarks that awareness is very important, collaborative efforts are very, very important, and the academia and industry interaction and the gap what we perceive between academia and interaction should be bridged properly, and it can be bridged only with the effort of each and everyone, all the stakeholders involved in this particular ecosystem. So there are many things which need to be done from our side as well as from the government side. And with this remark, I will thank, because not many people are there. So especially I'm not going for the valedictory session. This we consider as a valedictory session itself. And final remarks, concluded remarks, we have already taken from all of you. And thank you very much for attending this program, accepting our invitation, very short notice. You have accepted and you have given your very, very valuable time to us and for the deliberation, and triggering this MPVS 2021, because we are going to have larger discussions in December, that is from 22nd, 25th, when we'll have the complete very big conclave on the fab and fabless semiconductor ecosystem in Madhya Pradesh. So thank you very much. Thank you one and all for joining us in this program. And with this, we'll meet again in December, hopefully. Thank you so much.
Thank you very much.
Thank you. Thank you.
Thank you
Have
so
a nice
much.
Thank you very
all
much.
panelists and participants.
Thank you, everyone. Yeah. Yes.